Hello friends, hope you are having a fantastic day today. So now we are going to do a full course on the tree data structure, and trust me, after this you would become a master in all sorts of tree related interview questions. In this course we will learn what is the trees, what are different types, characteristics, when to use it, benefits, limitations, and what are going to be the time and space complexity of different operations, plus how to do different types of traversal, how to solve different kinds of questions. We are going to cover every single topic. Plus, we will learn 21 most asked, most popular tree related interview questions, where we are going to cover everything about trees, binary search trees, tries, and all sorts of different popular questions. So without any delay, let's get started. Tree is a very unique data structure, and if we see the categorization of tree, it is defined as a non-linear data structure. It is very closely associated with graphs with some differences that we are going to learn later in this course. Typically, we use trees to define relationships, and these relationships are typically hierarchical in nature. Now, these can be anything. You can think of a family tree, or you can think of a file system, or you can think of a structure inside a company or an organization and stuff like that. But typically, a tree usually comprised of two entities. First one is called nodes that we typically define by these circular items, and then second one is the edges between the relationships. And these relationships inside a tree are parent and child based relationship, where every single node can be a parent, or it can be a child, or it can be a both. So in this case, the very first child would be the root node, and then it has two subsequent children, and then these children can have children of their own, and so on and so forth. Now let's learn some terminology associated with trees that will help us understand better about different concepts. So first, let's understand that what are the different types of nodes available. Now very first one is a root node. Root node is parent to every single node. That is going to be the top node inside a tree, and this is going to be the gateway point through which we can enter tree and then traverse over all the other remaining values in different fashion. Next is a parent. Now any node can be a parent as long as it has child of its own. So in this case, this is a parent node, this is a parent node, this is a parent node, and this is a parent node. But these two nodes, or these three nodes, are not parent node because they don't have any children associated with them. Next we have child. So every single node can be a child node except root node, because root node would be sitting at very top, so it does not have any parents of its own. But currently, like, these two nodes are going to be children of the root node, then these two nodes are going to be children of this particular node, so on and so forth. So that can keep on going on and on. Next is a leaf node. So leaf node are the nodes that sit at the very bottom of the tree that does not contain any child of their own. So these are defined as the leaf nodes. Now the concept of subtree. So subtree can be part of any existing tree. So we can define that for any particular parent. So for this particular root node, we can say that this is one of the subtree of this particular node because it is part of its hierarchical structure. Same way, for this particular node, it only contains this node as part of its subtree, nothing more than that. Then there is a concept of height of the tree. So height of the tree is the longest distance we can make for any particular node from its root. So in this case, if we have to calculate height, at this level height would be 1, at this level height would be 2, and now notice we still have one more node at this level, so height is going to be 3. So in this case we can define height to be 3, even though we still have nodes that are going to be at lesser heights. Then we have depth of a tree. So depth of a tree is that for any particular node, what is the distance from its root node. So we can say for this node, the depth is going to be 2 because it is 2 steps away from the root node. Same way, this node is going to be 1 step away from the root node. So the depth of this node is going to be 1. And last one is a degree. So degree is defined by the number of child any particular node has, or any particular tree has in their structure. In this case, we can define that this node has a degree of 2 because it has 2 child. Same way, this node has a degree of 2, but in this case this node only has degree of 1 because it just has 1 child. So these are the terms that you will need to understand. Now let's learn that what are the different types of trees available. First one are the general trees. we can have a root node, and then it can have any number of child of its own from 0 to n. It can have one child, some nodes can have like 5 childs, some node can have just no child at all, some nodes can have like 50 child, so on and so forth. So there can be many relationships, and these can be very complicated, but we see all sorts of scenarios where we need to implement trees like this. Second one is a very restrictive tree that is highly used in technical interviews and also in real life, and that is binary tree. So binary tree has a simple formula that every single node must have at most 2 child or less than 2. So let's say in this case, this is going to be an example of a binary tree where we have nodes like these, where each of the node either has at max 2 child or less than 2 child. And this is like a good example because every single node either has 2 child or less than 2 child. Next one is a ternary tree. This is just for an example sake. In this case, every node are going to have 3 child at most, nothing more than that. So they can have 2 child, 1 child, or no child at all, but overall not more than 3 child. So this is a very similar example to binary tree, and same way we can define as n array tree. So where n can be any value. If we define n to be 5, then at any given moment, any particular child can have at most 5, any particular node can have at most 5 children and nothing more than that. So there can be many examples. And then there is a special type of tree, that is binary search tree. This contains a very special property where we are going to have a scenario where the value is going to be determining the structure of the tree. And of course this is a binary tree, so at most every single node can have either 2 or less than 2 child. Okay, that is a given fact. But on top of it, for every single type of node value, we are going to follow a strict principle that any particular value that is currently present on the left child has to be less than the root node, and any particular value that is currently present on the right child has to be greater than root node. So root node, the value is going to be that left child is going to be lesser than the root node, that is going to be lesser than the right node, right side node. And let's see an example of this in action. Let's say currently we are given a value 5 as a root node. So we can guarantee that no matter how many entries are currently present on the left side of it, all of these entries are always going to be less than 5, value number 5. Let's see an example of this. Let's say we can have a node like this, that is value is 3. Once again, for this 3, we are going to follow the same principle that everything on the left of the 3 is going to be less than 3. So this can be value 2, and then this can be value 1, and then this everything on the right of this 3 has to be greater than 3. So this, let's say this value is 4. Now we can think that 6 is also greater than 3. So can we put 6 over here? No. Why? Because we are still following the same principle all the way up to root level. So even though this value is going to be right of this particular tree, it is still going to reside on the left side of this particular 5 tree. So this value also has to be less than value number 5 as well. So this value can be 4. And same way on the right side, we can follow the same principle where every single value is going to be greater than 5, but there can be some like variations on its own. So let's say that this value is currently 8. Then the left of 8 is going to be value number 6. The right of 8 is going to be value number 9. And then the value at the right of this 6 can be value number 7, because notice now in this case for 8, every single thing on the left of the 8 is still going to be lesser than 8, and where we are following the same property. So now notice that if you traverse this particular tree in like this fashion, then you will find a sorted entry. And let's just try to quickly see that the very leftmost value is going to be the smallest value, and then its subsequent way. So we are going to traverse like left, then if there is nothing left on the left, then we are going to iterate its root, and then we are going to iterate its right child. And this traversal mechanism would actually allow us to get a sorted result or a sorted value for all the values that are present, and we are intentionally maintaining this property. So now I went a step ahead and actually just showed you that what does a traversal mechanism looks like, and this is actually an in order traversal. Don't worry about the word. I'm going to explain this in very much detail in subsequent parts. But remember that we can have a binary search tree that is going to allow us to have a sorted property being stored amongst different values that are currently present inside the tree. Now let's quickly learn that what are the different types of binary trees, because sometimes there can be questions being asked from these topics. So first one is a full binary tree where every single node either has 0 child or 2 child. So we can notice an example like this where this particular node has 0 child. Apart from that, and also this node has 0 child, this node has 0 child, but apart from that every other node has exactly 2 childs at the moment. We never have a scenario where we have only one child hanging. Okay, next one is a complete binary tree where all the levels are completely filled except the last level that is filled from left to right. So we can notice that, okay, this level root is completely filled, this level has 2 child, that is completely filled. Now this is the last level, so all the nodes are filled from left to right, and then we have one node that is currently not present. So basically there can be many examples. Next is the most beautiful type of tree, that is called perfect binary tree. So all the internal nodes has exactly 2 children, and last level is all leaves that are completely filled. So basically this is like the most good looking tree out there, that where every single node has exact 2 child, and then leaf node has no child at all. So this is perfect binary tree. And then we have a balanced binary tree, which is actually a very popular LeetCode problem that we are going to solve later on. But over here the thing is, height difference between left and right subtree is at most 1, nothing more than that. So we can notice that for this particular node the subtrees are going to be this one and this one, and we can see that the height of this particular subtree compared to root is going to be 3 for this node, and then for height of this is going to be 2. So at most we have difference of 2. But if we had one more node like this, then the height of this would have become 4 and this would have become 2, so that would not work. So that is like an example of different binary trees. Now for this tree data structure, we will need to find a way to iterate over all the nodes and then try to find the meaningful information. So there are different tree traversal techniques available to us. We are going to learn all of these in depth. So they are in order, pre-order, post-order, and then an extra one, level order traversal. We are going to use this example. So notice that this one I have taken as a binary search tree as part of the example, but overall it makes no difference on whatever type of tree we are trying to traverse over. So first one is an in-order traversal. We follow the technique that first we are going to traverse the left child. So as long as left child exists, we are going to keep on going in that direction. Then we are going to visit the root node, and then we are going to visit the right child of the node. And notice that root comes in between left and child, and that's why it is defined as in order traversal. Position of root is defined as what it is. So notice that currently we are going to be starting our journey at the root node. We have a left child, so we will go to the left child. Once again the left child also has a left child, so we'll go to that left child. And now notice that this does not have any more left child to visit. So now we are going to mark this node or traverse this node. So first node we are going to visit is going to be value number 1. Then we are going to continue our journey in the same fashion, and we are going to go back because this does not have any more subsequent children. Now we are at this position number 2. Once again we will follow the method of left, root, and right, but notice that for this particular 2 we have already visited left node, so now we can visit this node. So then next node would be 2, and it still has a right node that we haven't visited, so we will once again visit node number 3 and mark it visited. Then for this, now notice for 3 it does not have any subsequent children, so we will go back. We already visited 2, so now we will go back again. Now this 4 we haven't visited, but we visited all of its left child, so then we will visit 4. And now after this we will start visiting its right subtree or right child. So then we are going to come at value number 6. 6 also has a left child 5, so we will visit 5 first, and then we will visit 6, and then we will visit 7. So notice that because this was a binary search tree and we did in order traversal, we basically sorted all the values that are present inside the tree. So look how beautiful it looks. Now let's understand the pre-order traversal. Now the positioning of root slightly changes. First we are going to visit the root node, then we will visit its left child, and then we will visit its right child. And so now let's logically start iterating. Now notice that the entry point towards this iteration is going to be through the root node. So first we are going to visit node number 4 over here. After visiting 4, 4 does has left child. So then we will go to the left child. Once again, we are going to follow the same method and we will visit node number 2. Then we will go to left child and we will visit node number 1. Now after visiting this does not have any more children of its own. We will go back. We have already visited 2, but it does has a right child that we haven't visited. So we will visit this. And then once again we will go back. We have already visited this, and now we will repeat the same thing with its right subchild. So first we will visit node number 6, then we will visit node number 5, and then we will visit node number 7, and this is going to be the visited path. Same way we have Postorder Traversal. Now this one is slightly different because first we are going to visit left child, then we are going to visit its right child, and then in the last we are going to visit the root node. So as long as left or right child exists, we will have to visit both of them. So our entry point would be at the starting position 4. It does have a left child or left children and right children, so we will have to visit each one of them. We go to 2. Once again it has left child, so we will have to go and we commit value number 1. 1 does not have any child of its own, so now we will visit 1 as the first node. Then because remember we will go back, but this for this root number 2 we still have a right child that we haven't visited, and remember the order is left, right, and then root. So we'll visit the right child, and then we will visit node number 2 because we have visited all of its entry. Once again we will go back. Now though for this 4 we have visited everything on the left, we haven't visited the right subtree, so we will repeat the same process. We will go down to 6. 6 still has a left child that we haven't visited, so we will go to value number 5 first. After that we will visit value number 7 first, and after that we will visit value number 6, and in the end very last value would be visited, value number 4. So this would be the post order traversal. And last one is a level order traversal. We can also define this as a breadth first search as well approach, because we are going to go down in breadth for any particular node. So once again we are going to start iterating in the root, but now we will iterate level by level from left to right. So first we will visit node number 4, then we would visit its child, so node number 2 and node number 6. Then we will visit all of these values from left to right fashion, so 1, 3, 5 and 7, so on and so forth. This is also another technique that is pretty popular with basically graph related problems, but can also be applied to tree problems as well. Now let's understand that what are the different operations we can do on trees and what is going to be the time complexity. Now the binary search tree is a special case, and the regular trees are a separate case. So we will treat both of them slightly differently, and I will provide time complexity for each of them. In the example I have only shown you binary search tree, but it can be true for regular trees as well. So if you have to search for any particular element in a binary search tree, it is going to be very simple because we are simply moving away for 50% of all the nodes in one single go. If I have to search for node number 3 at root position, I simply have to check that whether 3 is less than 4 or not. If it is less than 4, then I can only need to check in this portion. I can completely eliminate all of these values. So that is going to be very powerful. So basically for binary search tree, the search operation is going to take on an average log n time, so which is pretty fast, significantly. But for any regular tree where we don't have such structure being maintained, it is going to take big of n time in the worst case scenario. Same way for insertion, it can be typically done in log of n time because we need to find where we need to add that value, and we can do it quite quickly. Sometimes we will have to adjust the existing nodes, but overall on an average case this will work in log n time. But for regular scenario, now how you are inserting the value is also a concern. If you are just inserting value at any position randomly, we can typically do it in big of 1 time on an average case. But if you need to add it only on the available leaf nodes with some condition, in the worst case scenario this can become big of n time for different tree operations. Same way for deletion, it is going to be log n time, but for this one it is going to be big of n time because first we'll need to find the value where it exists. So finding will take a lot of time. And traversal will take big of n time no matter what, because we need to iterate over every single node that is currently available. So these are the common operations that you can typically do with different trees, and it has different time and space complexities. So typically trees and graphs fall under the same categorization and both deals with relationships. The only difference is with trees, all the nodes are going to be connected, and all the nodes are guaranteed that they won't be forming any particular cycle. So there are no cycles in a tree and all the nodes are basically connected. Graph does not have any such conditions, which means we can have a graph that looks pretty similar to a tree, but we can have some more nodes that are basically not connected with each other, or we can have graph that has all the nodes connected but it can have some cycles as well. So trees does not have any such kind of condition, and typically for trees we are only dealing with parent child relationship, so there is no room for cycles. Now there are two pretty popular type of trees or variations of trees that has real use cases, and they are quite popular with all sorts of popular applications and interview questions. First one is a structure called tries, where we have a parent child relationship, but this is typically working in tandem with strings, and for each of the string every single character is being treated as if it was a node inside that particular string, and then it has subsequent children of its own. So let's say if I have to talk about a string that looks like ret, that is going to store the value for ret, then I would have a root node that is going to be empty, then it is going to have a subchild that contains value r, and then another subchild, and then another subchild. Now let's say that I want to create another value that is rattle. Then in this case, for this I'm also going to have one more variation where this is going to be pointing towards a null value. This is where it defines that this is one of the variations of the word, and then it is also going to have subsequent words as t, and then l, and then e. And same way you can store bunch of different applications, and then there is going to be a null value over here to point that this is also a full word on its own. Now you can imagine that there are thousands of applications or companies that are currently using this principle to generate something called autocorrect, where based on your current input we can autocorrect or auto suggest that whatever you are trying to type, and then automatically adjust those values. You can think of applications in all sorts of mobile and web and iMessages and WhatsApp. They all use the same principle, so you can imagine how popular this technique is. Now next one is a heap. So heap contains a very special type of property where it uses a balanced binary tree, and it can have two variations. So one variation is a min heap and second variation is a max heap. Both of them basically has a simple property that they are going to be a balanced binary trees. Apart from being balanced binary trees, they are, for a min heap it is always going to maintain the smallest value that we currently present inside the given all the sort of trees. So even if we present 50 values, the topmost element is always going to be the smallest value, and for some reason if we decide to pop that topmost element out, then automatically it would self adjust and find the second smallest element and bring it at the top. And opposite to that is a max heap, where it automatically tries to maintain the biggest value and it stores it in at the very top of the tree data structure or at the root position, where we can very quickly fetch that top element. So this has a lot of different applications. Now I'm not going too much in depth about what heap is and how does it work, because I have created a totally separate course on heaps as well that you can go and check it out. But basically this is a very popular type of variation of trees. Now speaking about benefits of trees, it has a lot of different practical application. You can use trees in file structures, you can use them to define family trees, you can use it to define hierarchical structure of any particular company, website, organization, different web pages, web crawlers, how they are connected with each other, relationships between any two entities. So all of these things can be very efficiently defined using trees. On top of it, you can also use trees to implement important concepts such as tries and AVL trees, red black trees, and heaps that are going to be having their own set of applications. So you can build things like autocorrect or auto suggestion bots. You can also create your own system where you are constantly tracking what is going to be the maximum and minimum entries at any given value, and then that can have major implications in stock related algorithmic trading, things like that. With the boost of AI, we are constantly building predictive models that are going to have multiple different way of potential answers, and they all can be connected with each other. So for in order to generate those kind of system, trees are also a beautiful mechanism to do all sorts of things. Plus, because tree has a lot of different variations, they can be applied by different applications and different variations of trees. So you will have to understand all of them and how to implement them. And on top of it, there comes the complexity associated with the tree. Because it is a non-linear data structure, understanding it is not quite straightforward. Implementing is also challenging. So there are a lot of issues associated with the data structure being non-linear and also very strict in terms of its policies and how it is being implemented. So you will need to understand that. Plus, traversal can be a big issue. If this is not implemented properly and correctly, then it can grow very large very quickly, and then it can lead to all sorts of time and space complexity issues. So you will have to be very careful that under what scenario you are trying to use trees to solve your problem, and can there be better alternatives out there. But overall, a fantastic choice and excellent in terms of technical interviews, because you will see all sorts of questions being asked from trees. So this was my introduction towards you for the trees. Now let's try to understand all the 21 most asked, most liked, and most popular LeetCode problems. And trust me, after solving all of these, I can guarantee you that you would become master in all sorts of tree questions for sure. So without any delay, let's get started. So the LeetCode problem we are going to solve is called balanced binary tree. Now we can see that this one is a LeetCode easy problem and also one of the most liked problems on LeetCode. The problem statement is quite straightforward, that we are given a binary tree and we need to determine that whether it's a height balanced binary tree or not. So the question is, what does height balanced tree means? It's actually quite straightforward. Height balanced tree means that at any given moment, the height of left subtree and the height of right subtree, if they do not difference more than 1, so which means that there is the maximum difference of heights is like 1 or 0. If that is the case, then we can say that this one is a height balanced binary tree, okay, or balanced binary tree. But if we identify, so let's try to understand. In this case, currently this one is our root node. Now if we see the left subtree, we can see that the height of this left subtree is 2. For the right subtree, the height of this right subtree is 3, which means the difference between left and right subtree is no less than or equal to 1, which means this one is a balanced tree or like height balanced tree. But in the same scenario, let's imagine that if we had one more nodes like this, then the height of this right side binary tree is going to be 4. Meanwhile, this left subtree is still going to 2. So if we do the difference of the height, we get the answer as 2, which is definitely greater than 1. In this case, we can say that now this binary tree is not a not a height balanced binary tree. Okay, so this is what we need to determine. Now this is like a very straightforward problem. Basically, at any given moment, we need to check that for any given node, what is the height for both left and right subtree, and this we can calculate very easily by simply traversing over the given tree in like any BFS or DFS fashion. And once we do the traversal at any given moment, we will have to keep track that for any particular root node, what is the height of its left subtree, what is the height of its right subtree. And if the moment we identify that the difference is actually greater than 1, then we can clearly say that this is not a balanced tree. If we identify that we iterate over the entire tree and we did not find that the height to be greater than 1 at any given moment between left height and right height, then in that case we can say that this one is a balanced tree. So that's it. This is all what we need to do. The approach is quite straightforward, and the idea we are going to use is that we need to traverse over the given binary tree. So for traversal, we know that there are iterative methods and recursive methods. Let's try to do it recursively. So recursively, we are simply going to iterate over the given tree. we need two items for the recursive case. First recursive condition is the base case. So base case is going to be that if the given current node is equal to null or zero, then we have basically exhausted every single child that we can visit for that particular tree. So we can do that. What is going to be the recurrence call that we need to make for the recursive level, that we are going to check that for any particular root node, first we are going to traverse its left child and then we are going to traverse its right child. So that is also good. Now while traveling, the moment we enter a new height or a new left child or a new right child, we are going to have a counter that is going to keep track of the left height, and we are also going to have a counter that is going to keep track of the right height. We are going to update it sequentially with every single level that we are increasing, and during every single update we are simply going to check that if the difference between left height minus right height, and we are going to do an absolute difference. So we don't care about which one is greater, as long as the delta is greater than 1. The moment we find this one, we can say that this one is an invalid or not a proper height balance binary tree. And if we reach to the end, we can say that this one is a height balance binary tree, and we can return this answer very easily and very simply. So the approach is quite straightforward. If we see time and space complexity, in this case the time complexity is simply going to be big O of n, where n is the number of nodes that are present. For the space complexity, because we are using recursion, we will have to induce or create a new recursive stack, so that might increase the time complexity to big O of n. And if you try to do this recursively, you can also do this in big O of 1 space complexity as well. But I don't think like any interviewer is going to have any issue of you using recursion, because that is a great way to save some time. And now let's quickly see the coding solution for this one. So if we see the solution, it's quite straightforward. We need to return a Boolean answer that whether the given tree is balanced or not, and in the input we are given the root. Now first we check for our base case that if the given root is equal to null, we can simply return true. If that is not the case, we are going to calculate the left height and we are going to calculate the right height. For that, we are going to use a helper method called getHeight, and we are going to pass in the root value. Now inside the getHeight method, we are also going to check recursively that whether if the given node is equal to null, we can return 0. If that is not the case, we are once again going to recursively call the same method for the left child and for the right child, and at every given instance we are simply going to calculate the maximum height we have been able to find both for left height and right height, and we are going to add +1. So this is going to give us the height at any given left subtree and right subtree that we are going to fetch values over here. Then we are simply going to have our math.absolute formula that if the difference is greater than 1, then we can simply return false. If that is not the case, then we simply need to say that yeah, if this given tree is balanced. So that's it. This is the whole solution. We can simply run the code, and then I think it should be working fine. Okay, seems like our solution is working okay. Let's submit this code. And our code runs 100% faster because there are very few test cases. So this is pretty awesome. Now, once again, this whole solution is actually posted on our GitHub repository that you can find over here. Now, this GitHub repository contains hundreds of very popular every single LeetCode problem that you can imagine, and for each and every problem I have also provided that what is the LeetCode problem statement for that particular problem, what is the Java solution, and for some reason if you cannot understand the solution on your own, you can actually go to the video solution as well. I have provided the link. So this is a great resource for anyone trying to prepare for LeetCode or DSA problems. The other thing is, I also want to show you one more resource that I have created, or not the LeetCode one, but the document that I have been able to curating. Now this document contains two very important lists. First list is the most popular and liked technical interview questions of all time. Now over here I have created a list of 130 questions. For each of these 130 questions, I have divided them based on the topic that you need to prepare. And I have also provided the key important information that how many times that particular question has been asked at what type of company. So this will help you in a couple of ways. Number one, you would be able to understand if you're targeting any specific company, you can find that how many times that question has been asked at that company. Number two, Based on just looking at the question, you can understand that how important that question in general is. So some questions have been asked like literally hundreds of times by many top tier companies. So you should be able to identify that as well. And each of the topics are distributed based on like easy, medium and hard LeetCode problems. So that is one option. Second one is the LeetCode 150 list that I'm currently working upon. So this is like the 150 most asked questions list created by LeetCode. That is an addition to blind 75. Now this is also a very pretty and very important list. Once again, all the questions are based differentiated based on topics. We can also see that for most of the questions, I'm trying to go through them and generate solutions for them as well. So yeah, if you want, you can also check out this resource. Maybe it can be helpful with your prep journey. Okay. So the LeetCode problem we are going to solve is called Symmetric Tree, and we can see that this is a LeetCode easy problem and also a very well-liked problem on LeetCode. The problem statement is very straightforward. We are given the root of a binary tree and we need to check that whether this binary tree is a mirror of itself or not, which we can see it from the example. Where notice that ignoring this root node, if we compare the subtrees of this root node, we can see that they are exact mirror copies of each other, which means this left node is same as this right node. Once again, this left node is same as this right node. And once again, this right node is same as this left node, which means we need to check that for any single given tree, whether this symmetric property is true or not. And this is actually very simple to do. So we are just going to do what we just used to explain this problem. If we understand we are given the root, then since this is a binary tree, it can either have a left node and right node, and once again this left node can also have a left node and right node, and same goes with the subsequent trees, and there can be many layers, as many layers as we want. The only condition we are checking is that for any single root value, we can only say that the tree is symmetrical if its entire left subtree is also symmetrical with entire its right subtree. And in that case, we need to check that whether the left child is the same as right child. And once again, even at this subchild level, we need to check for the grandchildren. So once again, even at this level, we need to check that whether this left tree is same as this right child, and also this right child is same as this left child. If that is the case, then we can determine that this is a symmetric tree, and we can keep on repeating or going down as many levels as we want, but the core logic remains the same, which means number one, we are doing two things. Number one, we are taking a bigger problem and we are actually breaking down into sub problems, and we are keep on repeating the same process for all of its children. So we are going to be using recursion to solve this problem. That is number one thing. Now number two thing is that we know in the recursion we need two items. Number one thing is that what is going to be the base case. So base case is quite simple. If any particular child does not have any more children, or if there does not exist any left or right node to check, then we can get out of the loop. And if we do get out of the loop and everything remains the same, which means we can return that this is a symmetric tree. That is option number one. Option number two is that at every given moment, we need to have a recursive function based on which we are going to be making our recursive call. And what is going to be the recursive function in this case? That at every single root node, we need to check that whether the left child of root is same as the right child of root or not. And we are going to be keep on repeating the same process. Once again, at the root node, we are going to check that whether the left grandchild of the root is going to be the same as the right grandchild of the root or not. So this is going to be our base case, that the left child is equal to right child and right child is equal to left child. This condition has to be satisfied, and then only we can keep on repeating the same process in the recursive manner. And basically that's it. So just the way I explained that, let's understand this with some example. So suppose we are given a value like 5, and then we are given subsequent values 3 and 3, and once again we are given further subsequent values. Let's assume like 4 5, and then this is also 4 5. So is this a symmetric tree? Yes, this is a symmetric tree because both of these values are same, this is also equal to this one, and this is also equal to this one, which means in this case we can return true. If we are given some other value, let's assume that over here we are given one extra child like 6, then we cannot complete the recursive call because this right subchild still also has a left subchild, but that is not present over here, so we can say that this is not symmetric. But in this case, if we did had another child like this, then we could have said that this is also symmetric. So this is the logic that we are going to apply. Now let's see the coded solution for this one. So first, this is the definition of our tree node, where every single node has a value. It has a left child and it has a right child. Now let's see our solution. So for our isSymmetric method, we need to return true or false or boolean value, and in the input we are given the root of the given existing tree node. Now first we are going to check for the edge case, that if the given root is equal to null, we can simply return true. If that is not the case, we are actually going to call our recursive method that is called isMirror, where we are going to pass in the left child and right child of our root node. Now let's see the recursive method isMirror. So as an input, we are having two tree nodes. So first condition we are checking is that if the given left is equal to null and right is equal to null, so both of these entries are null. If that is the case, we can simply return true, that saying that the tree is symmetric. If that is not the case, we are also going to check that if only one of them is null and the other one is not. If that is the case, then the symmetry has been broken down, so we can directly return false. If none of these cases are true, which means we still have to perform our iteration. So first we are going to check that if the given left dot value and the right dot value, so value of this left node and the right tree node, if both are same, then we are going to recursively call this isMirror method. For this isMirror method, we are going to take the left child of this left tree and we are going to compare it with the right child of this right tree. And same way, in the next iteration, we are going to compare the right child of this left tree with the left child of this right tree. So I know that this portion might look confusing, but if you just try to understand this using the image, things will become much more simpler. And I forgot to mention one thing during the code, that this code actually runs in big O of n time, because we are simply iterating over every single node just one time, nothing more than that. And in terms of space complexity, this is also going to be big O of n, because in order to fulfill this recursive stack, we might have to use big O of n space. Okay, so let's try to run this code. Okay, our solution seems to be working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is awesome and pretty good. So once again, I would be posting this solution in the GitHub repository where we have, which contains all of the LeetCode problems that we have solved so far. Also, I wanted to show you one more thing that might be helpful for your preparation. That is this Google document that I have created, which contains information about some of the popular courses that I have created. But this is the most important part. This is the collection of 130 most popular, most asked and most promising questions that has been asked at interviews. I have broken down these questions based on different topics. And also I have provided the information that how many times these questions were asked at specific companies. So this is going to be really helpful if you are targeting any specific companies, or if you are just targeting different topics, or depending on the different difficulty level. So if you want, you can start leveraging this, and I would be posting the link of this document inside the description of this video, so you can easily check it out from there. Thank you. So the LeetCode problem we are going to do today is called diameter of a binary tree. We can see that this one is an easy problem and also a very well-liked problem. The problem statement is quite straightforward. We are given the root of a binary tree and we need to return the diameter of the tree. Now the question is, diameter of a tree is the length of the longest path between any two nodes inside this tree, and we are told that this path may or may not pass through the root, but it's gonna pass through the root. Okay. Now the length of the path between any two nodes is represented by the number of edges between them. So let's try to understand that how does a diameter of a tree is being calculated. Let's say that we are given a tree like this. So in this case, what is the longest path we can make? Well, let's just give them the number. So 1, 2, 3, 4 and 5. These are the numbers of this given nodes. So we can see that the longest path over here is this one. So 3, 2, 1, and then 5. This is one path. Second longest path is once again 4, 2, 1, and 5. So in either case, the longest path we are able to make contains 3 edges. This is going to be the first edge, this or this, either one of them. Then this is the second edge and this is the third edge. So the answer is going to be 3, that this is what we need to return. Now the problem statement is quite easy to understand, but the thing is, how do we actually calculate the diagram? And if we start iterating over every single path and then try to find the answer, then this becomes a lot of complication. So we need to avoid that. And if you look at it from the other way, at any given moment or at any given node, the diameter of that node is nothing but the height on the left hand side. So left hand height and the height on the right hand side. That's it. This is all a diameter is. And we can see that in action over here, that the height on this left subtree is actually going to be 2, because this is the first level and this is the second level, and the height on the right subtree is going to be 1. So if we do 2 plus 1, the answer is going to be 3. So this is what we need to calculate. Now we need to understand that how we are actually going to be able to calculate that for any given binary tree. And for that, we simply have to iterate over any given tree, nothing more than that. Now iterating over the tree is actually quite simple, and we can use the common logic of recursion in this problem. Now for recursion, we need 2 items. First item is a base case. So base case in this case is going to be that if the current node, if that is equal to 0, which means we have reached to the very end and now we cannot go anywhere further. So then we start to do the backtracking. This is the first base case. Now what is going to be the recursive equation or recursive scenario? Well, recursive scenario is quite simple, that at any given moment or at any given node, the height or the diameter of that node is actually going to be the sum of the left diameter and the sum of the right diameter. And same way, even at subsequent left node, the diameter at that node is going to be sum of the left diameter and right diameter. And that's how we should be able to calculate the answer we are looking for. So in this case, the height on the left hand side is going to be 2. The height on the right hand side is also going to be 2. So the longest path we are going to be able to make is going to be of size 4. And we can also see some examples of that. So one of the longest path starts from this node and then once again to this node, and once again to this node, and then once again to this node, and once again to this node. If we see the number of edges included, this is the first edge, this is the second edge, this is the third edge, and this is the fourth edge. So this is exactly what we are looking for in terms of finding the answer. So we also found out the recursive solution, that the diameter at any given node is going to be the sum of the left node and plus sum of the right node. Okay, and then we can have a recursive function to iteratively recursively call our entire tree and then return back the answer. So this is actually going to be the whole solution. We are simply iterating over the tree, calculating the height, and whatever the sum of the height is, we simply return that. If we see time complexity, in this case, the time complexity is going to be big O of n, where n is the total number of nodes that are currently present inside the tree, because we will have to iterate over every single node. And in terms of space complexity, well, this is also going to be big O of n, because we are using the recursion, and in order to store the recursive stack, we might use big O of n space. So if you want, you can also do this problem iteratively, and in the iterative solution, we actually don't have to do or use the stack. But the only reason I am using the recursive solution is because it's good to do it like recursively. It's small amount of coding and also looks cool. Okay, so now let's quickly go to the coding. So the coding solution is quite straightforward. We are going to initialize our variable maximum diameter, and we are going to have our method diameter of the tree, from which we are going to call our get height method for left and right subtree for the given root element. Okay, now this our get height method is our recursive method. So let's quickly see what is happening. As a part of the base case, we are having the scenario that if the given node is equal to null, we need to return 0. If that is not the case, then we are going to find the left height and the right height. For both, we are going to recursively call the get height method with the left child and with the right child. Now for every single position, we will have to check that have we reached a new maximum diameter. So for that, we are going to do a simple equation of the current maximum element or maximum diameter we have been able to find. If that is greater, or if we find that the current left and right side subtree's height is greater than the current maximum diameter we have been able to find, then we need to update the max diameter. If that is not the case, then we can simply leave the max diameter as it is. Next, we need to return the height that we have been able to find. So in the end, we are simply going to return 1 plus the maximum value of either left height or the right height. And why are we doing 1 plus? Because at any given root node, we also have to consider the node by itself before propagating the height to its previous level. So that's why this 1 plus is there. Okay, with every new level, basically we add one value to the height. And this is the solution. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. So our code runs 100% faster than all the other solutions, and that's because the code actually operates on a very simple principle, and it runs in 0 milliseconds. So that's why it's 100% faster. It's nothing magic. Now, once again, the coding solution is present inside our GitHub repository. Let me quickly show it to you that this is the GitHub URL where we have actually stored hundreds of LeetCode questions and their answers. These are some of the most popular questions in the entire world. These questions has been asked at tons of different companies multiple times. So for each of the problem, you can go ahead and see we have the Java file for that. You can go and find the LeetCode link. If you don't find, you can also find the subsequent video solution, and also a list of most asked problems at the FAANG companies, which is this list, which contains a lot of important LeetCode problems. They have been differentiated based on the topics, and for each of the topics I have provided that how many times they have been asked at different top tier IT companies. So there are 130 of most fabulous questions that I have been able to find. Then also I have solved most of the LeetCode 150's problems, and they are also provided over here. So both of these resources are amazing. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to invert a binary tree lead code problem, and if we see some of the companies where I want to work at who have already asked this question, there are companies like Amazon, Facebook, Google, Apple, Bloomberg, Microsoft, Uber, Goldman Sachs and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode easy problem and also very well liked problem on LeetCode. Basically, we are given the root of a binary tree and we need to invert the tree and return its root back. So let's try to understand this with a couple of examples. First of all, we'll take this example. So over here, we are given a tree that looks like this, where this 2, 1 and 3 are part of the tree, where 1 is the left child and 3 is the right child. So if we invert this tree, we will get an answer that looks like this, where 2 remains the root because it is the root node, but this 3 that was originally the right child will become the left child, and this 1 that was originally the left child will become right child, and this is what we need to return. Let's take a little bit more complicated example. So over here we are given the root to be 4. Now we are given that the left child and right child of this 4 is actually 2 and 7, and further down we are given more left child and right child for this 2 and 7 as well. Now if we invert those all of them, we will actually get a result that looks like this, where 4 remains the common, this 7 that was originally the right child will become the left child, and this 2 that was originally the left child will become right child, and same thing will happen for these leaf nodes as well, and this is the answer we need to return in the answer. This is what the problem is asking us to do. Let's see that what would be the different approaches to solve this problem. Before we come up with the optimal solution, let's understand a very important concept. Suppose this is one of the kind of a binary tree we are given and we need to invert this tree. Well, if we see over here, we are given a root node, then again we are given some left child and we are given a right child. Now further down for this left child and right child, they also have the children of their own and they also form a bigger binary tree. So at any given moment, suppose we are given this root node, we are given this left child and we are given this right child. So if we want to invert this tree, all we have to do is whatever this right child is and whatever this left child is, if we just swap them or if we invert them, basically we are at least done with this root level and with this left child and right child level. Now again, if we further break down that, suppose this is the left child, now we are treating this left child as a root. So suppose now this is the root and this is the left child and this is the right child for this root. So again, if we want to invert them, what we can do is we can take whatever the left subtree and right subtree is. So in this case, for this root, the left subtree is going to be this, the right subtree is going to be this. If we swap them, essentially we have taken care of up until this level for this inverting part, and same way we can keep on repeating the process. So now this becomes our root. Again, we flip these two values, and even for this level we have taken care of inverting the binary tree. So this is what exactly I'm suggesting us to do in order to solve this problem, that we starts breaking this given input into bunch of smaller inputs and start inverting binary tree in that manner. So the idea is that for every single time we will have a root node, we will swap its left and right child. Then again, for if there exists any left or right child, we will repeat the same process and keep on swapping those values, which means that we are actually doing the changes recursively. We can actually solve this problem pretty efficiently. Let me quickly show you how. Suppose this is the input we are given and we are trying to invert this binary tree recursively. So what we are going to do is, suppose we will take initially this as the root node, and for this root node we actually have a left child and we actually have a right child. So what we are going to do is we are going to swap its values, and we are going to swap the entire left subtree and entire right subtree. Then at any given moment, as long as we have some nodes, we are going to keep on treating them as different root nodes, and then we will keep on flipping their values or their children's values, and at the end we should have a completely inverted binary tree. So let's see that in action. So first of all, this is the root node and this is the left and right subtree. So what we are going to do is we are going to swap the values. So we will have a tree that looks like this. Okay, so far treating this as root tree, we have actually swapped these left subtree and right subtree, and we will get a tree that looks like this, where you can see that this value 3 and 2, they are actually inverted, but their subsequent children values, they are not inverted, and we will still have to repeat the same process. So let's see that in action. So now again, what we are going to do is we are going to treat this 3 to be root child, and we are going to repeat the same process with the 6 and 7. So if we invert them, we will get a tree that looks like this. Now we are going to treat this 7 to be the root node. If we treat this 7 to be the root node, actually it does not have any children, which means we don't need to flip any more values. Now again, we will treat this 6 to be the root node. If we treat this 6 to be the root node, again it does not have any more children, so we can skip that. Now we will treat this 2 to be the root node. So if we treat this 2 to be the root node, it has children, so we will have to swap their values, and we will get a value that looks like this, and we would have taken care of both of them. Now again, this 5 and 4 does not have any children, which means we can't do anything about it, and then in the end this is going to be the answer we need to return. So we can simply return the root value, and basically we would have inverted the entire tree recursively. So that is the approach we can use as an optimal solution. There is also one more way to iteratively approach this problem, but the thing is, I believe that for tree kind of problems, the recursive approach is better than the iterative approach. Let me know in the comments if you want to see the iterative approach as well, and I can make a separate video on that. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over every single tree to invert them. Now if we see the space complexity, well, at any given moment, because of the recursive function, we might have to store bunch of different node values, and that would depend on the height of the tree. So basically the space complexity is going to be big O of h, where h is the given height of any binary tree. So because we are going to solve this problem recursively, first let's create the terminating condition, that if the given root is actually null, we can return. If the given root is not null, we are going to make the recursive call for right and left values. So for right tree, we are going to make the recursive call to the same function with the right child. Same thing we are going to do for the left subtree. After that, we are going to replace the values of left and right subtree. So now that should have taken care of all the cases, and now we can simply return the root value. And that should be it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. and our solution is actually pretty efficient. It's actually 100% faster than all the other solution, and that is because the runtime is actually 0 millisecond. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do maximum depth of binary tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Google, Facebook, Apple, Bloomberg, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem and also very well liked problem on LeetCode. If we understand the problem statement, basically we are given the root of a binary tree and we need to return its maximum depth. Now we are also given the definition of what a maximum depth is. It is basically the number of nodes along the longest path from the root node down towards the farthest leaf node. That is the depth of the tree. And if we try to understand this with an example, suppose we are given a tree over here that looks like this. In this case, the maximum depth is going to be 3. Why? Because the nodes at the root level is currently at position 1 or height 1. The root at this level is at depth 2 or height 2, and root at this level is actually at depth 3. So in this case we need to return 3 as the answer, because 3 is the maximum depth we can get from this root node. So let's see that what would be the different approaches to solve this problem. Okay, suppose this is the input we are given and we are trying to find the maximum depth for this particular given tree. Suppose this is the root of the tree. If you want to find the maximum depth for this tree, the answer is going to be 4 because of these two nodes. We can see it clearly over here, that over here the value is 1, this is 2, this is 3, and this is 4, and this is the answer we need to return. The question is, before we return this answer, we will actually have to build some intuition behind it. And the intuition is, suppose at this position number 5, if we want to determine that what is the maximum depth over here, well, what we can do is we will check on the left side, we will check on the right side, and whatever has the greater number of nodes on either side, we will actually take that as maximum depth and we will do it plus 1. Well, in this case, the 6 and 7 both are located at the same position. 6 and 7, none of them has any children, which means that over here we can determine that this is actually 1 and this is also 1. So on the left side and on the right side, both values are actually 1. So what we can do is we can do 1 plus 1. So 1 plus 1 will give us the answer that the maximum depth at position number 5 is going to be 2. So in this case, okay, we have found the maximum depth over here to be 2. Well, if we take this value number 4, well, at this value number 4, it does not have any more children. If it does not have any more children, which means we can determine the maximum depth in this case is going to be 1. Well, now we have these two values. That now based on these two values, it becomes pretty easy for us to identify that what is the maximum depth at this position number 2. All we will have to do is we will take whatever the maximum value amongst these two is. Maximum value is actually 2. So what we can do is we can do 2 plus 1, and 2 plus 1 is actually going to be 3. So we can determine that 3 is going to be the maximum depth we can achieve at this node number 2 if this was to be the root of the given tree. And for this position number 3, the maximum depth we can achieve is only 1 because it does not have any more children. So that is a given fact. Now we have these two information. Now it becomes pretty easy for us to identify that what is going to be the maximum depth at this position number 1. And all we will have to do is take the maximum amongst these two values. So maximum value is going to be 3, and all we need to do is just plus 1. So if we do 3 plus 1, we will get the answer 4, and 4 would be the correct answer in this case, and that is what we are going to return. So the maximum depth we need to find, we can simply do it by using this method. Well, now if you see, for this particular solution, we are actually able to achieve this solution, but what we are doing is that at any given position, we are seeing that what is the left max value or right max value, and whichever is greater amongst either one of them, we are taking that and we are adding 1. Well, now again we are repeating the same process, that we are taking the left max and right max value, and again we are adding 1. So which means that in order to solve a bigger problem, we are actually solving a smaller problem and then again a smaller problem. So basically we are doing it recursively, and that is how we are going to solve this problem using recursion, which is very powerful and it is highly used in different kinds of tree problems. So that is how we are going to solve this problem, and this would be the optimal solution we can use. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n, because we will have to iterate over every single element in order to get the answer. And if we see the space complexity, in this case the space complexity is also going to be big O of n, because we might have to store all the values inside our recursive function. And this approach is actually very good. It works as expected. There is also one more approach which uses stacks, and that does not use recursion. It actually use iterative function. So let me know in the comments if you want to see the stack solution as well, and I can also explain that. But for now, if you show this recursive solution in any interview, the interviewer would be more than happy. So let's move on to coding now. So first of all, we are going to take care of a edge case. If that is not the case, we will have to call our recursive function. First of all, we are going to have an integer called left max that is going to take care of the left subtree for any given root position, and we are going to call our recursive function again. And same we are going to do for the right subtree as well. We are going to create a parameter called right max. And in either case, all we have to do is simply return whatever the maximum value we are able to find, and then we will add 1 to it. And this should be it. Once we get out of the loop, our solution would be done. So let's try to run this code. Okay, seems like our solution is working. Let's submit this code. And our code runs as expected, and it's actually pretty fast compared to a lot of other solutions. So I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do same tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Google, Bloomberg, Apple, Microsoft, Facebook and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and as the name suggests, same tree, the problem is self-explanatory, but let's go over it. That basically we are given two roots of a binary tree called P and Q, and we have to write a function to check if they both are same or not. So let's try to understand this with couple of examples that are given over here. Here we are given this two trees P and Q, and in this case we can see that both of these are 1, both of these are 2, and both of these are 3. So we can say that okay, they are actually same, and we can return true in this case. But for the second example, if we see the P and Q values over here, for 1 is same, so root values are same. But if we see over here, this is actually 2 and this is actually 2. Despite being the same value, the positioning is not same, because this is actually the left child of this given P tree, and this is actually the right child of this given Q tree, which means that these two are not same. So in this case, we will return the false, and this is what we have to achieve. So let's see that what would be the different approaches to solve this problem. So solution of this problem is actually quite simple, and if we see the approach one, we are going to use an iterative approach. In the iterative approach, what we are going to do is we are going to iterative over both of these given trees in the same manner, and we are going to keep on checking subsequent nodes of every single position. At any given moment, if we identify that any single node does not match, we can return false immediately, and if somehow we can reach out to the end of the tree and iterate over every single nodes, we can return true in this case. So let's see that in action. So first of all, we are at this P, for this P and Q tree, currently we are at this root position, so we will check that value, and both of them are actually 1, which means we are good so far. Now we are going to iterate over on the left side. So on the left side, this value is actually 2 and this value is also 2, so again we are good. Now again on the left side, this value is actually 3 and this value is also 3, so again we are good so far. Now we go back, and now for this position number, we also have a right subtree, or so we will check that right position. This is 5 and this also has a right position, which is also 5. So far we are good. Now again we go back to this root node. We still have this right side that we haven't traversed, so this node is 4 and this node is also 4, so again we are good. And at the end, this node is 6 and this node is 6. Now we don't have any more nodes to go back to, so essentially we have traversed over all the nodes inside given both the trees, so we can return true in this case. And this is the approach we are going to take. Let's see what would happen in a scenario where trees don't match up. So here I have drawn that example as well, that over here all of these nodes are same, but actually this node and this node, these two are not same. So because these two are not same, the moment we iterate over all of these nodes and eventually we would reach to these positions, we can return false immediately in this case. So this approach would work as expected. And if we see the time and space complexity in this case, the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over every single node inside the given tree for both P and Q trees. The space complexity would be big O of log n. That is because this is a binary tree. Well, in the second approach, we are actually going to solve this problem recursively. And the idea is at any given moment we have to identify that whether two trees are same or not. The thing we are going to do is we are going to compare their root nodes. If they both are same, we will have to compare their entire left subtrees, that they have to be the same, and also we will have to compare their entire right subtrees that as they also have to be the same. And if that is the case, we can define that tree to be the same. But if we take a look at for the left subtree, again we are going to repeat the same process, that even for the left subtree we are going to compare the root nodes. If they both are same, then we are going to compare their left subtrees and their right subtrees to be the same. So essentially we are doing the same thing repeatedly for different kinds of input, and recursion is the best way to approach that. And also your interviewer is going to expect you to do this recursively, because that would be more efficient way of doing it. So let's see that in action. So the idea is at any given moment we are going to compare the root node. So over here root node is same. Because root node is same, we will have to check that whether the left subtree is same and right subtree is same or not. So first we will do the left subtree. So now for the left subtree we have these two trees for P and Q respectively. So again we will check the left node. So left node is this 2 and this is also 2. So they both are same. Now we are going to check the left subtree and right subtree again. So this both of these are 3, so we are good. Now we will have to check the right subtree. So right subtree is also 5 and 5, so again we are good. Now again, so far we have calculated the entire left portion, but we haven't calculated the right portion. So now we will do that. So again for the right subtree, this value is 4 and this value is 4, so again they both are equal, so we are good so far. And then these values are 6 and 6, so again we are good so far. Now we have iterated over every single node recursively, that is the important part, and we have found all the values to be the same. So because they were same, we can return true in this case and everything is good. And at any given moment, suppose we identify that any single node does not contain the same value as its counterpart, then the moment we are comparing these two values, we can return false immediately, and that would be the solution for this problem. If we see the time and space complexity in this case, the time complexity is also going to be big O of n, because we will have to iterate over every single value, and the space complexity is going to be big O of log n. So the time and space complexity is not different than the iterative approach, but recursive approach just is a lot less coding, and I will also be showing that in the code. So first of all, we are going to check that if the given P and Q both are null. If both are null, we will have to return true, because essentially they both are same. If that is not the case, and if any of either P or Q is null and the other one is not null, then in that case we will have to return false. And if both values exist, then we will have to compare their values. And if both values are not same, we can return false immediately. If that is not the case, we will have to iterate over left and right subtrees of a subsequent P and Q trees. So now we are going to make our recursive call. And that's pretty much it. Let's try to run this code. Okay, seems like our code is working as expected. Let's submit this code. And our solution runs pretty efficiently. It's actually 100% faster, but if that is not the case, because runtime is 0 millisecond, that's why it's showing 100% faster. I would be posting this in the comments so you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do subtree of an another tree LeetCode problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Google, Facebook, Apple, Bloomberg and Tesla. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and basically we are given the roots of two different binary trees called root and subroot. Now we need to check that whether there exists a subtree of this original root tree where the structure is completely same as whatever the subroot binary tree that we are given. If that is the case, we will return true. If that is not the case, we will return false. So let's try to understand this with an example. Basically, we are given two different binary trees called root and subroot. Now over here, we can see that the structure of the subroot, which contains the root value as 4, left child as 1 and right child as 2, where 1 and 2 does not have any more children of their own. The same structure is also present in this example as well. And because it is a subtree of this original root binary tree, we can return true in this case. So now let's take one more example to make things a little bit more clear. So in this second example, we are also given two different binary trees. Now if we see the structure of the subroot, we have a node 4. It has a left child and right child of 1 and 2 respectively, and they don't have any more children of their own. Now if we see this original root, we can also see a similar structure, and I'm focusing on the word of similar, not exact same, because in this case we also have 4, 1 and 2 present. The thing is, notice that this 2 actually has another node or another left child 0 that is present over here, which is not the case in this scenario. So because this is not the case, we cannot say that these two are same, and these two are actually not same. So in this case we will return false. And basically we are trying to see that whether one tree is a subtree of another tree or not. So that's why the name of the problem is subtree of another tree. It is self-explanatory. And now let's see what are the different approaches to solve this problem. So this is the root and subroot we are given. Now over here we are trying to see that what would be the optimal solution for this problem, and basically we can clearly see that the answer in this case is going to be true, because this 9, 1 and 2 is also present as a subtree in this original root tree. So that's why we can return true in this case. The thing is, let's see that what is going to be the strategy. Well, the idea is we are actually going to iterate over this given root tree in BFS fashion. Now if you don't know what BFS is basically breadth first search, and you can see more details about that in this video I have done previously. Now let's focus on the problem at hand. So the idea is that at every single time we are going to iterate over this root node, and we are going to iterate in BFS fashion, which means we are also going to iterate its neighbors for every single node. Now at every single time we are going to compare it with this subroot tree, and the moment we find a match, we are going to iterate over both the trees in BFS fashion. So let me quickly show you what I mean by that. So first of all, in this root tree I'm going to iterate over this root number 5. Now this root number 5 is not same as this root number 9, so which means I can't do anything over here. I have already iterated this value. Now I'm going to iterate its children. So first of all, I'm going to iterate over this root value 8. So this 8 is again not same as this 9, so we can ignore this case. Now we are at this position number 9. So this 9 is actually same as this 9. So because these two values are same, now I'm going to do BFS traversal for both of the subroot and root trees. Now from this 9, if I see the BFS traversal, basically I'm going to go to the left child. So left child in this case is 1. So again I'm going to see the same thing. Even in this case the left child is also 1. So yeah, I'm good up until this point. Now I'm going to go to the right child. This is 2, and the right child in this case is also 2. So yeah, again I'm good until this point. Now I'm not going to stop my traversal. I'm going to keep on iterating till I find all the null values. So in this case this 1 does not have any children left or right. So in this case I'll encounter a null value. So I'll try to see the same thing over here. So over here this does not contain any subchild of its own as well. So this is also null. So I'm good up until this point. Now if I try to see this portion, so this is also null, and this is also null. So because all the values are same and I found no other children that I can iterate over, in this case I can simply return true. Now there are two ways to do this problem. I can do it iteratively or I can do it recursively, and if you know my videos, I like the recursive method better, so I'm going to show you the recursive solution. Now let's see one more case where the answer is going to be the false. So suppose for the same example we do everything right, but over here this 2 actually has a subchild called let's just say 7 over here. Now because this 2 has a subchild called 7, now the moment I am done iterating these values and I don't find anything, I'm good up until this point. But now at this portion, at this node 2, I'll find a value 7 over here, but when I try to find the same value over here, I won't be able to find, and because I won't be able to find, I'll return false. Now the time complexity is actually going to be big O of m plus n, Why m plus n? Because we will have to iterate over all the nodes that are present inside this given tree root and subroot, and m is the number of length of all the nodes that are present over here, and n is the number of length of all the nodes that are present in this subroot. And if we see space complexity, well, basically because we are doing it recursively, we might have to iterate over all the values, and the space complexity in the worst case could be m plus n as well. And now let's move on to the coding. So before we start working on each subtree method, first of all, we are actually going to have to create a new method where if we pass in the value of any root node and subroot node, it can determine that whether both values are same or not. So first let's do that. So we created an isSame method which takes in the value of two tree nodes. Now first of all, we are going to check that if both values are null, which would be the terminating case for our recursive call. So if both values are null, we can simply return true. Now if that is not the case, we will also have to check the scenario where one value is null and other value is not null. If that is the case, we will have to return false. Now there is also one more thing we'll have to check, that and that is the value of this s and t. So if the value of s and t, if they are not the same, we can return false immediately. And if everything is not returned by this point, which means that the value of s and t is same, so now we will have to check the left subtree of s and left subtree of t, and same thing we'll have to do for the right subtree of s and right subtree of t. So let's do that. Now from our main method is subtree method, first of all we are going to check that if the given root is null. If that is the case, we can return false immediately. So if that is not the case, we will have to call our isSame method for this root node and subroot node. So let's do that, and if we get the answer to be true, we can return true immediately. Okay, so if this does not return true, which means this current root and subroot, they are not the same. If they are not the same, we will have to iterate over this node root for its left child and right child to see if they are same with this subroot or not. So let's do that. So now for that, we will have to call this isSubtree method again, and we are going to run bfs on this tree node root. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Our submission failed. Let's try to diagnose. Oh, in this isSame method, we will have to check that whether the answer of both of them, if that is true or not. So we'll have to use AND condition. Let's try to run the code again. Okay, seems like this is working. Let's submit this code again. Okay, and now our code runs perfectly fine. It's faster than a lot of other solutions, and I would be posting this in the comments so you can check it out from there. Thank you. The problem statement is called count good nodes in a binary tree. We can see that this one is a relatively new problem, a medium problem, and also a very well-liked problem. On top of it, this has been asked at tons of different companies. So let's pay some attention that what the question is asking us to solve. Basically, we are given the root of a binary tree and we need to return the number of good nodes in a binary tree. The question is, what the heck is a good node? Well, a tree node is deemed good if in the path from root to that particular tree node x, there are no nodes with value greater than x. If that is the case, that node is a good node. So let's try to understand this with an example. Currently, we can see that there are 5 different nodes or 6 different nodes in this particular tree. Now we are being told we need to find the good nodes. The definition of a good node is that path from root to any particular node. If that particular node contains the maximum value, then it is deemed good node. So let's try to see what are the good nodes, starting with the root. Now root in itself is a good node because path from root to root is the biggest value. So we find one good node. Okay. Now let's consider value number 1. What is the path between root to value number 1? This path. Is 1 the largest number on this path? No, which means 1 is not a good node. Then let's consider the path 6. So for 6, the path is 5, then 1, and then 6. So in this case, 6 is the largest number from the direct path to the root, which means 6 is also a good node. So let's mark that. Once again, now we found everything we could. Let's try to move to next value number 5. So is 5 a good node? Yes, 5 is also a good node. Why? Because the definition of 5 is that from root to that particular x, there are no nodes with value greater than x. So in this case, the nodes we have is value number 5, 1 and 5. So there are no other nodes that has value greater than 5, which means 5 is still a good node. So we will also mark this as good. Then we will jump to value number 7. So once again, the direct path from 5 to 7 is this one. So in this case, 7 is the largest node. So 7 is also a good node. And next value is once again 7. So once again, even in this path 5, 7 and 7, there are no values greater than this 7 as well. So 7 is also a good node. So in this case, in total, we found 1, 2, 3, 4 and 5 good nodes amongst these 6 nodes. So we need to return 5 as the answer. And this is what the problem statement is asking us to solve. So now let's try to understand the logic on the solution we can build for this particular problem. The logic is quite straightforward, that we need to iterate over the given tree in some fashion, and we will have to keep track that around this iteration, what has been the largest value we have been able to find so far, keep track of it, and using that particular value, we are going to make some important judgment calls. So the logic we are going to do is that we will have to iterate the given tree in depth first search fashion. Why depth? Because we will have to keep track of the entire path from root to any particular node. So for that, we will have to go into the depth first search order. Now, what are the considerations? Number one thing is, first we are going to check the root or at any given position, because first we are checking the root, then we are checking for its left entire subtree, and then right entire subtree. Same thing we are doing at every single level, that first we are checking that for this particular root, whether it is the largest number. After understanding this, we are checking its left subtree and then right subtree. So basically we are doing the pre-order traversal in this case. And pre-order traversal is quite straightforward. The logic is root, then left, and then right subtree. So we are once again going to do a pre-order traversal, in this case in depth first search fashion. We are going to keep track that what has been the maximum value we have been able to find inside the current path. If the current node is equal to or greater than the maximum value we have been able to find, so in this case we are going to deem this node as a good node. So we also need a variable to store the good node as well. So let's assume that, okay, we are going to have our count variable to store all the good nodes we have been able to find so far, and this is the whole solution we need to create. So let's try to understand, or let's try to iterate over our given solution, and let's just arbitrarily give some values to these particular trees or these particular values. So in this case, we can see that these are the different values. Now let's start with value number 3. 3 in itself is a good node because we are doing the depth first search pre-order traversal. We are going to take care of the root first. Okay, now we took care of this root. Now let's take care of the left child. So left child is once again 1. So once again, even at the left child position, we will have to follow this position of root, left and right. So once again, now left child in itself is a root. So we have value number 1. What has been the, and also we have our maximum value we have been able to find on the current path. So maximum value so far has been 3. This value is 1. So current node is not greater than maximum value, which means this is not a good node. Now we will need to check for the left pointer. So left pointer is once again 3. So 3 is same as the maximum value on this path we have been able to identify. So we are going to mark this 3 as the answer that we have been able to find so far. Now 3 is also going to be a good node. So we are going to add our count of good nodes. Now we are going to do a backtrack. Now for the backtracking, once again, we have a right node that we haven't checked. So we are going to take care of the right node as well. The value of the right node is 5. So currently at this particular position, the right node is actually greater than the maximum value we have been able to identify. So we are going to store, once again, count this 5 as a good node as well. Apart from doing that, we will also have to update the maximum value we have been able to identify. But this particular node does not have any subsequent child nodes of his own. So because it does not have any child node, there is no point in updating the value of the maximum node. But say for an example, if we did had one more child like this, where we need to check for the value of this node number 6, then this 5 would have been the maximum value we have been able to identify so far, but that is not the case. Once again, coming back, Now we took care of 5 and we took care of 3. It does not have any children. We are going to do the backtrack. We already took care of 1, which means now we have to taken care of this entire left child. Once again, in our pre-order traversal, we took care of the root very first, then we took care of the left child. So this is the entire left child portion of this root. Now we need to take care of the right child. So once again, we are going to do the same thing. We are at position number 4. So we are going to first check that whether 4 is a good node or not. So in this path, the current maximum value we have been able to identify was value number 3. So 4 is a good node. But in this case, because we are checking for the subsequent children of 4, we will have to update the maximum value we have been able to identify along this path to value number 4. So this is the maximum value we have found so far. Next value is value number 2. So 2 is not is less than the maximum value we found. So 2 is not a good node. So in this case, we found in total 4 good nodes. So we are going to return 4 as the answer. And that's it. This is the whole solution that we need to return. Basically, we need to understand that why we need to use DFS in this case, because we are going in one particular direction. We will need to keep track of the maximum value at any given track. And we also have to do the pre-order traversal because we are following the principle of root, then left, and then right. And you can do this recursively or iteratively, it's up to you. We will see that in the coding. If we see time complexity, it's pretty straightforward. It's going to be big O of n because we are iterating over every single value. In terms of space complexity, if you use the recursion method, it will take big O of n. If you use iterative method, it would not take big O of n. And let's quickly see the coding solution for this one. Okay, so we are going to use a helper method called count good nodes to keep track of the good nodes we have been able to identify. And we are going to pass in the root value we found so far. Now this count good nodes is actually going to return an integer value that defines that how many number of good nodes we have been able to identify for this particular root node. Then we are in the initial input, we are just returning like the minimum value possible, because root in itself has to be greater than that. So root is going to be the first good node. Okay, now we are going to check, okay, that we are taking in as an input the tree node and the maximum node so far. We are checking for an edge case that if the given node is equal to null, we can simply return this 0. If that is not the case, we need to initialize our count to 0. Then we are going to check that if the given current node value is greater than the maximum value we have been able to identify. If that is the case, then we are going to update the counter to 1. And we are also going to update the maximum so far to the current node that we just found out. Once again, we are going to repeat the same process for the upcoming subsequent left child and for upcoming subsequent right child, and we are going to add the values of the left child and right child to our existing count value as well. So whatever count they come back with, we are going to add them to our existing count, and in the end, whatever the final count we found, we are going to return that, and that would be written as part of the answer for this one. So that's it. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster, which is pretty awesome, because this has to be some of the fastest code, because the runtime is also not 0 millisecond. So we are doing something really awesome over here. Once again, solution is posted on our GitHub repository. So feel free to go ahead and check it out. Thank you. So the LeetCode problem we are going to solve today is called find leaves in a binary tree, and this one is actually a LeetCode premium problem, and that's why you see that the UI looks slightly different. Now let's try to understand the problem statement. We are given a binary tree and we need to collect trees nodes as if we are doing the following, where we are collecting and removing all the leaves inside the given tree, and we are going to repeat this until the entire tree is empty. Now we all know that what does a leaf node in a tree looks like. Basically, the node that does not have any children is referred as a leaf node. So what we need to do is that for any given binary tree, we are given the root of it. We need to iterate over the entire tree, find that what are all the leaves that it currently has, collect every single leaves in one order, and then repeat the same process with all the remaining nodes. So in this case, we can see that at the beginning, these three are the leaf nodes. So we are going to mark these as the leaf nodes and we are going to collect them in the answer. So we will collect 4, 5 and 6 as part of the first set of leaf nodes. Then we would get rid of these nodes. Then once again, we would be left with another set of leaf node that are going to be nodes 2 and nodes 3. So that they would come in the second portion of like collecting leaf nodes. Once we get rid of them, in the end we will only be left with the root node, and that is going to be value number 1, and that is all what we need to return. So this is the whole problem solution. Now you can imagine that solving this problem seems quite trivial. All we are doing is that at every given instance, we are basically iterating over the given tree and we are trying to find that what are the leaf nodes. So we know that what is the condition of any particular node to define that it is a leaf node or not. Well, we can check that if for any particular node, if the left child is equal to null and if it's the right child is also equal to null, and the node is currently not equal to null, which means the node exists. So in that case, we can define any particular node to be a leaf node. So we know that how to identify a leaf node. Second thing is we need to store every single leaf nodes that we collect, which means we will have to create an array list where we are going to store bunch of different array list for every single piece of LeetCode leaf nodes that we found. Okay, that is second thing. Third thing is how are we going to iterate over the given input, and for that there are actually couple of ways, but in this case recursion would be a very good approach to reach out and solve this problem, because we know that in the recursion we basically need to repeat the same process, and same goes in this problem as well, that first of all for this entire given root node we will need to find the leaf nodes. Same thing happens when we do go to the left child and right child. Once again at the left child and right child level we need to find the leaf nodes. So currently this one is a leaf node in itself, so we will mark it to the answer. At the right child level, left child level, once again we will still repeatedly try to find the same things. Once we find all these three leaf nodes, we will mark them into the answer, remove them from the existing tree, so declare that the current node is equal to null, and then once again repeat the same process from the root. So let's try to understand the solution I'm suggesting in action. Let's just give some arbitrary values to these particular nodes. Okay, so in the recursion, we know we need two items. We need a base case. So base case is quite straightforward. The definition on how to define any particular leaf node that we just saw, that if the given left child is equal to null and the given right child is equal to null for any particular node, we can define that node to be null. That is the first base case. Second base case is that if the node in itself is null, then we are simply going to return null in that case. We don't need to do anything. But if we do identify at any particular moment that if left child and right child both are null, then we need to add that particular node to the answer array list that we have created for the current set of leaf nodes. Okay, and what would be our recursive case? So recursive function is going to be quite simple, that if the node has some left child and if the node has some right child, then recall the same recursive method once again until we reach this base case, and we would have added every single value inside the answer. So let's try to see the solution in action. First, we are at this root node. Currently root node does have left child and does have right child. So once again, we are going to do the recursive function. So if we apply the recursive function, we are going to reach over here. Once again, for left child, we once again find it does have left child and right child. For right child, it does not have any other values. So and also for these subsequent values of left child and right child, we see that they don't have any children of their own, which means all of these are identified as the leaf node. So we are going to mark values 4, 5 and 3 in the answer as first set of leaf nodes. After declaring them, we are going to eliminate them from the given input. And now once again we are going to repeat the same process starting from the root node. So currently for this root node, it still has a left child. Once again for this left child, it does not have any child of its own. So this is going to be another set of leaf node. And in the end, we will also get rid of this one. And finally, we are at the root node. So once again, recursively, we find out that root node does not have any children. It meets the base case. So we are going to add it to the answer as well. And this is the answer we are going to return in the end. So logically, this is a very simple tree traversal problem. but with every single traversal we just want to repeat the same process by eliminating few nodes and keep on doing it again and again till the entire tree is empty. So this is the whole solution. If we see time and space complexity, in this case the time complexity is simply going to be big O of n, where n is the total number of nodes present, because we will have to do it for each one of them. Even for the space complexity, in order to maintain the recursive stack, it is going to be big O of n, and also we need to create an extra array list to store the answer, and that is going to be completely dependent on the total number of nodes that are currently present. So overall this is a very good question and a good amount of time and space complexity. If you do encounter this in any of your interview, don't get afraid or don't worry, because this is like a simple approach on how you can traverse the tree and find the best solution that is asked. Now let's quickly see the coding solution for this one. So here is the coding solution for this one. Once again, we are running it in an online compiler and not in the LeetCode, because this is a premium question. So here is the definition of our tree node. It's just a standard tree node. Now let's quickly take a look at our class solution. So first of all, we are going to create a method that calls collect leaves method that provides in the root of the tree, and in the answer we are going to return an array list that contains list of values where we have all the leaves connected based on the edge cases for every single iteration. Now first of all, we are going to define the result where we are going to return as part of the array list, and we are simply going to run a while loop that while the given root is not equal to null, we are going to repeatedly do this, where first we are going to create a simple array list to collect leaves in that particular iteration of that tree. So this is going to provide us the leaves level by level. Then we are going to provide the results by calling the remove roots method, where in the remove leaves method we are taking in a tree node, and we are also taking in the current set of leaves as an input, and this is going to be our recursive helper method, where first we are checking that if the given node is equal to null, we can simply return null. If that is not the case, we check that if the given node is a leaf node. If that is the case, we are going to add it to our leaves array list for now, and then we are going to remove it. And if that is not the case, both for left and right child, we are going to call the remove leaves method once again, and in the end we are simply going to return the node. So this is our helper method, where we are recursively iterating over the any instance of the tree based on the given node that we are provided. And once we return that back to root, we are simply going to add those results that we found inside the leaves as part for the in the result array list that we have created. In the end, we can simply return the results. Now I have also created a main method and just created like some dummy cases to see that where what is the answer we find. And we can see that the root node is 1, and then it has a left child 2, and the right child is 3, and once again for left child it has 4 as its left child and 5 as its right child, and so on and so forth. So if we try to run this code, we should be receiving the answer as expected. And we can see that in the first iteration we remove 4, 5, 6 as leaf nodes, then we remove 2, 3 as second set of leaf node, and lastly the root node of 1. So this is the answer. Once again, the solution is present in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve is called binary tree right side of view. Now we can see that this one is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. The problem statement is actually quite straightforward. We are given the root of a binary tree. Now we need to imagine that as if we are standing on the right side of the binary tree, and then we need to return the values that we see from the right side, and we need to return the top to bottom values. So let's try to understand this problem. Currently we have a binary tree over here. Now imagine yourself that as if you are standing on the right side of the binary tree. So from the right side of the binary tree, you can see only this portion of this given binary tree, which means currently you are only looking at these 4 nodes, and all of because this node is being blocked because of this one, and these 2 nodes are also being blocked because of this one. Okay, so in this case, what is your right side view or your right side vision of this tree? Well, first we need to return the answer in top to bottom manner. So first we are seeing node number 1, next we are seeing node number 3, next we are seeing node number 6, and lastly we are seeing node number 7. And this is what we need to return as part of the answer. Now let's first try to understand that what the answer looks like in each of these three different scenarios, so we have a clear understanding on what is being expected from our side. So if we take a look at this first tree, well, the answer is going to include, this is going to be the first node, this is going to be the second node, this node would be blocked, so we would not be able to see it, and then once again this node would also be blocked, so we will include this node. So these are the three nodes that we are dealing with. Okay, next, in this particular scenario, we can see that we need to return the right side view. The thing is, hey, there is no node on the right side of the tree. So well, in that case, we can still see the left side of the node as well. So we are going to include this node, and we are also going to include this node in our answer. Okay. And in the lastly, this scenario is slightly tricky. So of course, this node is going to be part of the answer, but then at this particular level, we will have to include this node. Once again, at this particular level, this one is the right child and this one is the left child, but still, because we are standing on the right side, we need to take the value that is closest to us on that particular level. So once again, this node, and then lastly, on this last level, we don't have any particular nodes, so we are going to use this node. Now in each of these three scenarios, we can see one very clear distinction in terms of answer. That is, we are seeing that at any given level, we will have to take one node from that particular level. We are going to select the node that is the last node in that particular level. That is the same case for this one, because this is one level, there is only one node, so this is the last node. Over here we have two nodes, but we are only going to consider the last node. Once again, we are only going to consider the last node over here as well. This one, there is no explanation needed. This one is slightly trickier example where we can, okay, so this one we understood why we take it. Amongst these two nodes, we are closest to this one, so we are taking it. Amongst these two nodes, even though these nodes are close to each other, we are once again closest to the right side node, so we are going to take it as part of the answer. And this one once again is still the last node at that particular level. So we are able to establish that for any particular binary tree, the right side of the view is simply going to be doing the level order traversal and finding that what is the last node at that particular level. So in either case, we simply have to do a level order traversal. Now level order traversal for trees typically refers as breadth first search. So we know how to do breadth first search. It's a very common and popular tree traversal techniques. If you don't know what breadth first search is, let me just quickly explain. We are at the root position. So what we are going to do is, for root position, we are going to put it inside a queue. Now we know the property of a queue, that it is a first in, first out type of scenario. For each level, we are going to iterate over all of the children that it has. And if it has the children, we are going to put them on the queue as well. And once again, repeatedly, we are going to keep on subsequently doing the same thing with their children as well. So logically, we would be iterating over in one particular level by level across the entire tree. And that is called breadth first search. So let's try to see our solution in action. So in this case, let me give values to these particular nodes. And we know that the answer in this case is going to be 1, 3, 6, and 7. But currently, let's say that this is our queue. Now in our queue, we are going to keep track of two things. Number one, that what is going to be the last element at any particular node. And number two, that for every single level, we will have to keep track of that at what level these particular nodes belong to. Okay. So we can very easily track that, because every time we add a new child, we can just mark it as like a new level that we are adding inside the queue. And apart from that, we can simply move forward as it is. So currently the first value is going to be node number 1. For node number 1, because it has children, so we are going to add node number 2 and node number 3 inside our array as well. Inside our queue as well. Once again, for both node number 2 and 3, they also have the children of their own. So for node number 2, they have 4 and 5. So we are going to add 4 and 5. For node number 3, they have 6. So we are going to add 6. And lastly, we are going to have value number 7, that is the child of node number 6. So once again, let me just add one more into over here, 7. So now we can see that I have color coded every single different level based on all the elements for that particular level, and in that particular color coded pattern we need to find the last element. So this is basically going to be by default last element, so we are going to add this to our answer. Next we have two values at this particular level, so we are going to pop this element out because we don't care. This is the last element, so once again we are going to add that to our answer. Once again we have three elements over here, we are going to pop each one of out, and the moment we reach to the last element we are also going to mark it as the answer. And then this is also the last element at this particular level, so once again we are going to mark it as the answer. And that's it. This is the whole solution. Now at first glance it looks complicated, but all we are doing is just doing the breadth first search in a common fashion and trying to find the answer. Now in this case, since we are standing on the right side of the binary tree, we are selecting the last element. But same can be said that if we are given a question where we need to find that what is going to be the left side view, where you are standing on the left side of the binary tree, same logic is going to apply. The only thing is now you are going to be dealing with the first entry that pops up inside of your queue for every single new level, and that is what you need to put it in the answer. So basically these are like two questions in just one question by just changing the direction of where you are standing. If you see time complexity, in this case this is going to be big O of n. If you see space complexity, this is also going to be big O of n, because we are using an extra queue to keep track of all the elements that we have iterated so far. Overall this is like a decent time and space complexity, because this you have to go through this in any of your tree programs unless it's a binary tree and you're trying to search an element. So now let's quickly see the coding solution for this one. Okay, so this is the coding solution. First, we are going to initialize our new array list to store the answer, and we are going to mark it as result. We are also going to check for an edge case that if the given root is equal to null, we can simply return the result. If that is not the case, we are going to initialize our queue, and inside our queue, we are going to populate the very first element, that is going to be the root node. Now we are going to iterate over the tree in the breadth first search manner by stating that while queue is not empty, do this. So first we are going to define that what is the current size of the given queue. Then we are simply going to have a for loop to run over the given queue, where we are going to keep on polling elements at every single position, and we are going to mark the last node of the current level inside the result that we are going to populate. Okay, then we are going to check that for this particular given root value, do we have any left child and do we have any right child? If we do, add the left child and right child to the current queue as well, and this is going to iterate over the entire binary tree in breadth first search manner, and we would have our result array list populated as well. In the end we can simply return results, and this is the whole solution. So let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. Few things can be improved in terms of space complexity, but anyways, this is a good enough solution. I would be posting this in the GitHub repository that we have created. Hello friends, we are not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do binary tree level order traversal LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Facebook, Bloomberg, Google, Apple, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary tree. Now we need to return the level order traversal for this binary tree, and we need to return the nodes values. Now we are also told that we need to return them in left to right fashion and level by level. Basically we are given a binary tree over here. Now for any binary tree, basically we always have two things. We have a root node or a parent node, and that parent node has some children nodes. So, and furthermore, this children node can have children of their own as well. So every time a new set of nodes are being added at the bottom, essentially we can define a new level being created. So if we see this example over here, essentially this is level 1, this is level 2, and this is level 3. And we need to return the nodes level wise from left to right. So let's try to understand this with this example over here. where we are given 3 levels. So this is level 1. These 2 nodes, they are located at level 2, and this 2 nodes, they are located at level number 3. So in the answer, first of all, we are going to return this node 3 because this is the only node at this level. There are no other nodes. Now at the second level, we have 2 nodes 9 and 20, and we need to return them in the same sequence of 9 and 20. And in the third section, we have 2 nodes 15 and 7. First we'll return 15 and then we'll return 7, and that is the answer we are going to return in this case. Let's see that what would be different approaches to solve this problem. So when it comes to tree traversals, there are mainly two subcategories. First one is a depth first search and second one is a breadth first search. Well, in the depth first search, we actually expand upon the depth of any given tree and then we keep on iterating over all the nodes. While in the breadth first search, we actually visit the root node first and then visit its children and then keep on repeating the same process. So in this portion, for depth first search, there are three further subcategories: Inorder, Preorder and Postorder, which I'm going to show you first, and then I'll explain you how breadth first search work. And in this problem, actually we are going to use breadth first search to solve this problem. So during the Inorder Traversal, basically first we visit the left side of the tree, then we visit the root node, and then we visit the right node. So first of all, for this root node, we will keep on expanding until the left node exists. So left node exists over here and then left node again exists over here, which means this is the first node we are going to visit. So we start our visit traversal at 4. Now 4 does not have any more children, which means we can't go downwards anymore, which means now we go back to the root node. So root node for this 4 is actually 2, and then we again expand on the right side. For this 2, we still have right side 5 that we haven't visited, so we will do that. Now again we have visited all these 3 nodes, so now we are done with these. Now we again go back to the root node, which is 1, so we visit 1, and then again we repeat the same process, left, root and right. So again we go on the right side. So this is the strategy for Inorder Traversal. Now for the Preorder Traversal, basically we follow the principle of root, left and right node, and this is the way we visit the node. So first of all, we are going to visit the root node, which is 1 in this case. Then again we are going to visit the left node, which is 2. Then again we are going to visit the left node, which is 4. Then again we are going to visit the right node, which is 5. Again we come back, and now in this case we again go back to this root node, which is 3. Then again we go to the left, and then again we go to the right. So this is the strategy for using a Preorder Traversal. Now for the post-order traversal, basically we follow the principle of left node, right node and then root node. So first of all, we are going to visit up until left node exists. So this is the leftmost node. So we are going to visit that first. So we start our traversal at this position number 4. Then we visit the right node, which is 5, and then we visit the root node, which is 2 in this case. Now after this, we actually don't visit this node 1 because for this node 1 there exists a right subtree that we haven't visited. So we again go to the right side, and again this also has a left node, which is 6. So then we visit the node 6 in this case, then we visit the node 7, and then after visiting the 6 and 7, then we visit its root node, which is 3, and in the end, after visiting all the nodes, we visit the main root node, which is 1. And this is going to be the traversal strategy for the post order traversal. So when it comes to breadth first search, we actually expand upon its neighbors or its children for any given tree rather than going in depth in any one particular direction. So if we see for this particular tree, the breadth first search traversal is going to look like this. So first of all, we are going to visit the root node, which is 1 in this case. Then we are going to visit its children. So its children are actually 2 and 3. So we are going to visit this node 2 and 3. Now for this left child, again it still has children of its own, so we are going to visit them first. So we are going to visit this node 4 and 5, and then for this node 3, it has children of its own as well, which is 6 and 7. Now in this case, we cannot further expand because this 4, 5, 6 and 7 does not have any children of their own. So we are done with the traversal. Basically we have iterated over all the nodes that were given. But if you see these nodes and the fashion we have visited them, it actually gives a very interesting perspective for the problem we are trying to solve. Well, first of all, we are visiting the node that is located at this position number 1. Then we visited its children, which are actually located at this level 2. So first we visited the level 1 node, then we visited all the nodes that are present at level 2, and then we visited all the nodes that were present at level 3. If we had any further nodes, then we would have visited them that were for the nodes that were located at this level number 4. So this breadth first search is actually a very good solution for the problem we are trying to solve, where we are trying to see that what would be the level order traversal for any given tree. Basically we are anyways iterating the nodes in particular levels, so all we will have to do is just simply make tuples of the levels that we are visiting and the nodes we are visiting at. So that is how we are going to optimally solve this problem. Now we are going to use the same tree that we have been using so far, and we are going to see that what would be the answer. So first of all, we will have to create an array list where we are going to store the answer. Now at any given position, whenever we start iterating over this tree and whenever we jump to a new level, we are going to create a new node inside our array list. So first of all, we are at this level 1, right? So now for this level 1, we are going to create a new node over here, which is this one. And for this level, because this node is located at level 1, we are actually going to create an entry over here. Now for this one, we are actually going to iterate over its children. We are going to call its children 2 and 3. Now because these are children of this node 1, they are actually going to be located at level which is whatever the level of this 1 is plus 1. So the level of this 1 is actually 1, so 1 plus 1 is going to be 2. So these nodes, they are actually going to be located at level 2. Now the moment we identified a new level, we are actually going to create a new node inside our array list. So over here we would have created this new node. Now in this new node, because we visited these values 2 and 3, we are going to actually add the value 2 and 3 over here. Now again we will have to further go down for this level 2 and 3. And remember that initially we only had this one node and we visited its children. Now again we have a node and we are visiting its children, and again we have a node and we are visiting its children. And suppose these had, if the new nodes, we would have visited their children as well. So basically we are doing the same work for different set of inputs, where initially this was a child but now this becomes a parent for these nodes. So we are basically doing recursion, nothing special in this. So now from this level 2, whenever we will call these left and right children, basically what we would have done is we would have increased whatever the value of level was for this value 2 plus 1. So this was located at level 2, which means these nodes, they are actually located at level 3. So now again we created a new level. So because we created a new level, we are going to create a new entry inside our array list, and then all the values located at this level, we are actually going to store them in this portion of our array list. So now first of all we are going to visit node 4, so we are going to add node 4 over here. Then from this 2, we are going to visit its right children, which is this node 5, so we are going to add 5 over here. Now we still have nodes that we haven't visited, so now we have this node 3, so we are going to first of all visit its left children, which is this node 6, and this is also located at level 3 because this 3 originally was located at level 2. So this is also because this is at level 3, we are adding it in the third portion or third placeholder inside our array list, and then in the end we are going to visit this node number 7 as well at the end. Now this does not have any further children, so we are good up until this point, and we can stop our traversal and return this new array list that we have created as the answer. So this is the approach we are suggesting, and if we see, we did the breadth first search traversal and basically we did it recursively. Now we could have done it iteratively as well, nothing special in there. So you can discuss with your interviewer what is the strategy you want to use, and 9 out of 10 times your interviewer is going to ask you to do this problem recursively because it's lot less code. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside this given node. And if we see space complexity, well, basically we will have to create we will have to make recursive calls, and that takes some space, and that space is actually dependent on height of the given tree. So space complexity is actually going to be big O of h, where h is the height of the tree. Now first of all, we are actually going to create a list of lists where we are going to store the answer, and we are going to declare it as a global variable because we are going to create a new method for our recursive call. So first of all, let me create this global variable called answer. Now we are going to create a new public method which is going to be acting as our recursive function, and it does not return anything. We are going to name it as order, and as an argument it is going to take any tree node and the level we are currently at. And now inside this method, First of all, what we are going to do is that whenever we are at any position or whenever we are creating a new node, basically we are going to add a new entry to our answer. After creating a new value for a new level, now all we will have to do is whatever this tree node is, based on its level value, we will have to add that value to our answer. Now after doing that, basically all we will have to do is for any single given node value, first of all we are going to check that whether it's left child and right child, if they exist or not. If they exist, basically we are going to call the same order method with this left child and right child, and we are going to increase the value of the levels. That is all we need to do for this order method. So now from this main method, first of all we are going to check for an edge case that if this given root is null. If this is null, we can simply return the answer. And if this given root is not null, basically we will have to call this order method with our root information and the current level that we are at. And now at the end, we simply have to return whatever the answer we get. Let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is actually pretty efficient compared to a lot of other solutions. And I would be posting this in the comments so you can check it out from there. Thank you. LeetCode problem we are going to explain is going to be binary tree zigzag level order traversal. This is a really popular problem, and this has been asked in some of the top tier companies such as Amazon, Bloomberg, Microsoft, Facebook, Apple, LinkedIn, Google, Samsung, Goldman Sachs, and TikTok. So that is why I'm paying my utmost attention. I highly urge you to pay your attention for this problem as well. If we see that this is a LeetCode medium problem and also very well like problem. Now in this problem, we are given the root of a binary tree, which means a binary tree means that any single parent can have at most 2 children, nothing more than that. So now we have the root of this binary tree, and now we need to return the zigzag level order traversal from its nodes values. So what does a zigzag level order traversal means? So first of all, before understanding the zigzag level order traversal, let's understand what does a level order traversal means. Level order traversal simply means that first we go through the first level, that is level 0, then level 1, then level 2. So if we see the level order traversal, first we would it go through value number 3, then second level, so that is value number 9 and 20, and then the third level, that is 15 and 7. But since in this case the level order traversal that we were making was pretty simple, we were going from left to right. So we went from here, we went to left to right, again from here we went from left to right. But in this case we are making our lives easier and we are going in the zigzag fashion because that is the current trend. And zigzag fashion is that first we start over here from left to right from the root node, then we go in the zigzag fashion. So we go like this, and now again we repeat the zigzag pattern, and now we go from left to right again. So for one level we go from left to right, next level we go from right to left, and again next level we go from left to right, and we keep on repeating the same process. So in this example, if you see, first we went through level 3 left to right, this was the value. Second we went through the right to left, so 20 and 9. So from after 3 we visited 20 and 9, and then we went through 15 and 7, and let's see what would be the solution for this problem. Okay, suppose this is the input we are given. Now first let's see what is the level order traversal going to be. First we are going to visit value number 1, then we are going to visit in this fashion, so the value is going to be 3 and 2, then again from this fashion, so value is going to be 4, 5, 6, and then again from this fashion, so the 8 and 7. This is going to be the answer for sure, we already know that. But how we are going to come up with the answer? In order to come up with the zigzag level, first we need to go through the simple level. How to go through simple level order traversal? Well, for what we are doing in a simple level order traversal is that we are iterating the parent, then we are iterating its child before iterating its grandchild. So in this case, first we are going to we are at this place, we are going to iterate over its child. After iterating both children, we are going to iterate its grandchildren or the children of these children. So first we would be covering this level. Then after covering this level, we would be going through the children of these nodes. And so going in this fashion, and again repeating the same process with this one. And this can be achieved using breadth first search because it's pretty simple to do. And this is how how traversal is done in trees using breadth first search. That is a level order traversal. So even in this case, we are going to use the breadth first search to run in a simple level. But how do we use breadth first search? Well, from our experience, we know that in order to use breadth first search, we need two items. We need a queue and we need a visited hash set. But the thing is, we only need visited hash set in a graph kind of a problem where there is an issue of us running in an infinite loop. There is no issue of us running in an infinite loop inside a tree. So we are not concerned about using a graph in this case. We are only going to use a queue. And currently, I'm just showing you how to do a level order traversal, and then we will do zigzag level order traversal. So first, let's just see the level order traversal. For that, we are first of all going to start at the root position and we are going to populate that value inside our queue. So this is currently value number 1. Now we are going to visit the children of 1 before visiting the grandchildren of 1. This is the whole logic of the BFS, that we are going to visit the children before visiting the grandchildren. So who are the children? Obviously 2 and 3. Again, we are going to add values 2 and 3 here because it has 2 children and we are going to mark them. Now we visited all the children of value number 1. So we are going to pop value number 1 out and we are going to put it in the answer that we traversed this part already, and now we only have values 2 and 3 inside the input. Now again for 2 and 3, 2 has children that we haven't iterated over. So who are the children of 2? 4 and 5. Mark them here, and same way get rid of 2. So 2 has been taken out, and now currently the entries are 3, 4 and 5 inside our queue. 3, 4 and 5. Again 3 can be kicked out by adding 6 at the end of the queue. We added 6 at the end of the queue. Awesome. Now 3 is also out. Currently the entries are 4, 5 and 6. Now even for the values 4, 5 and 6, starting at position number 4, it does not have any child. So 4 can be kicked out without any repercussion. 5 currently has a child 7. So adding 7 at the end and getting rid of 5. So we can put 5 over here. Again values are 6 and 7 in place. Again for value number 6, it has a child called 8, adding 8 in the end and getting rid of 6. And now after that there are only 2 values left, 7 and 8. Currently 7 does not have a child, so we can get 7 out, and also 8 does not have a child, so we can also get 8 out, and this would be the solution. But in this problem, what we did is we went in the normal level order traversal, not the zigzag level order traversal. So let's see how can we make zigzag level order traversal possible. Currently, what the concept we are using inside the queue is, currently we are using the first in, first out principle that gave us the level order traversal. But what happens is that when we move from left to right, this concept is absolutely true, that we can have like first in, first out, and that would give us the proper level order traversal. But when it comes to reversing, imagine that in this case, rather than getting 2, since 2 was already inside the loop before value number 3, if we pop 3 out before 2, then we would have been able to accomplish our mission. So since in this case we are going in the zigzag fashion, remember zigzag fashion is going to be like this, where on one iteration we are moving from left to right, next iteration we are moving from right to left, and again for the next iteration we would move from left to right, and we would keep on repeating in the alternate fashion till we reach to all the nodes inside the given input. So now let's see that what are some of the adjustments we can make to make our life so much more easier and fix this issue that we were having in the level order traversal. The solution is quite simple, and the solution is that whenever we have to find from left to right, we can use the concept of first in, first out. So this first in first out is going to use on these two occasions. But when we need to move in the reverse order or right to left, in this case we will have to use the concept of last in first out, because logically what was happening in this case is that logically we were traversing in last in left to right for every single one of them in the level order traversal. So typically we were going like 2 and 3, but imagine since 3 was last added, if we took the last in first to approach, then inside the solution we would have values such as this one. So 1 is following FIFO, first in first out. So 1 was added first and 1 was removed first. But for this particular position we are using the concept of last in first out. So even though 2 was in the queue before value number 3, we are going to have 3, that was the last value, come out before the value of 2. So 1, 3 and 2, such like this. Again we are going to use first in first out for this particular level. So the solution is going to be 4, 5, 6. That is pretty simple. But for these two, again we are going to use LIFO principle, and that is going to give us the answer of 8 and 7. Now if we see this sequence 1, 3, 2, 4, 5, 6, 8, 7, this matches with the original answer we wrote at the beginning, 1, 3, 2, 4, 5, 6, 8, 7, and this is the whole solution. So let me clean this up a bit, walk you through my solution, where we are simply arranging the way we are entering the values inside the inside the queue and popping the value out of the queue. Okay, so now we are going to have our queue. We are going to add all the entries, and the only simple thing we are going to do is whenever we have to move from right to left, we are going to pop the value at the from the end of the queue rather than popping from the beginning of the queue, because we are flipping between FIFO and LIFO principle. And the one data structure that is capable to do this is actually a DQ data structure in like both Java and Python languages. So you can use either one of them. Okay, so let's start iterating, starting from value number 1. 1 is placed here. Currently 1 has 2 child, 2 and 3. So we are going to mark 2 and 3 in this position. Currently for 1 we are iterating from left to right. So we are going to get the last in first out. So 1 would come out. Now the values are located as 2 and 3. Even for 2 and 3, currently we need to get them out in the zigzag fashion or right to left fashion. So for that, first we are going to pop it from the end. But before popping it from the end, we will first add the children of 2 and 3. So the child of 2 is 4, 5. So let's add 4, 5 here. And child of 3 is 6. Let's add 6 here. After doing that, we are going to pop 3 out first, and then we are going to pop 2 out first. So 3 and 2 has been out because 3 was value before 2. And again for 4, 5, 6 we need to do the same thing, but we need to do in the left to right fashion. So 4, 5, 6 are going to come out as themselves, but before that we are going to iterate through it their children. So 4 currently does not have a child, so we can pop it out without any repercussion. But 5 has a child, the value is 7, and 6 has a child, the value is 8. Again we pop 5 out. So popping 5 out should be simple, and popping 6 out should be simple as well, because we already took care of them. But for value 7 and 8, again we are moving in the right to left direction. So last in value 8 is going to come out first before 7 coming out, and in the end we would not have any values inside our queue, which means we can get rid of it. And now you see the traversal is being done in the level order and also in the zigzag fashion, and that is the most important fact, and this is how you solve this problem. Again, if we try to see the time and space complexity, the time complexity is going to be big O of V plus E, or vertices plus edges, or nodes plus edges, because we are using our BFS. And space complexity, since in order to use the BFS we will have to use a queue, the space complexity is going to be big O of V, or the number of nodes or number of vertices inside our given tree. And this is the whole solution. Let's see the coding solution for binary tree zigzag level order traversal. So first of all, for this one, we are given the method that to return a list of lists that contains the zigzag level order traversal of the given input tree, and as an input we are given the root node. So first of all, we are going to check for the edge case that if the given root node is null, we can return an empty new array list immediately. If that is not the case, first we are going to initialize the array list. Inside this array list, first for the first node, we are going to add the root node, and we are going to add a null node as well, and we are also going to use a new tree node linked list to iterate over the given input tree. Now we are going to mark the level list because every single level is going to contain a different set of answers, and we are going to use this boolean parameter to keep track that whether we need to traverse from left to right or right to left. So is order left is initially set to true, which means currently at the beginning we are moving from left to right. Now inside the while loop we are going to do our BFS function, where if this given boolean is order left is true, which means we are going to use the last in first out and add all the elements inside the level. If that is not the case, then we are going to use the first in first out and also add all the values that are present on that particular level. After adding all the levels, we are simply going to populate our result list based on the level list we have created, and then we are going to initialize a new level list for the next level, and again we are going to change the ordering from left to right to left for the next level. And after repeating the same process again, even for the next level, the ordering is going to be again left to right. In the end, after this BFS operation doing loop ends, we would have our result linked list populated, and we would be able to return that as the answer. So let's try to run the code. Seems like our solution is working as expected. Let's submit the code. And our code runs pretty efficiently compared to a lot of other solutions. And don't worry, I'm going to post the solution of this code inside my GitHub repository that is open to public, so everyone would be able to see that. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do construct a binary tree from pre-order and in-order traversal lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Microsoft, Amazon, Bloomberg, Apple, Uber, ByteDance, Google, Facebook and LinkedIn. So that's why I am paying my utmost attention. I hope you also enjoy the video. Now this is a very hated LeetCode problem, and let me show you why. This is from the solution tab of the LeetCode problem, where people have expressed their views very abruptly. Some people are saying why God why, some people are saying that it's time to leave for Himalayas, some people are saying that if you get this question they do not want to hire you and things like that. There are many other comments. The thing is, we do not want to focus on the negativity. Let's try to see that what is the approach to solve this problem, and then we are going to see that how can we be able to solve this problem if we encounter this in any interview, because our aim is to get into FAANG, not just dream about it. Now this is a LeetCode medium problem, but in my opinion this should have been a LeetCode hard problem. Now let's try to understand the problem. Basically we are given two integer arrays called pre-order and in-order, and basically they are the pre-order traversal of a binary tree and in-order traversal of the binary tree. Now based on these two arrays that we are given, we need to construct and return the original binary tree. So let's try to understand this with an example. So over here we are given as an input, we are given two different arrays, pre-order array and in-order array. Now somehow if we iterate over this pre-order and in-order array, there is only one combination of binary tree we can make, and which is this one. So that is the example that is given over here. Now let's see that what is going to be the different approach to solve this problem. But before we do that, the important thing in this problem is to understand that what is a pre-order traversal, what is the in-order traversal, and how can we use their properties to our advantage. So first of all, I'm going to show you pre-order and in-order traversal, how it works. So first of all, we are going to learn about pre-order traversal, and basically pre-order is a DFS kind of traversal, which is depth first search. If you want to know more about different kinds of traversal, you can check out my video over here. Now let's focus on the pre-order traversal for now. So basically in pre-order traversal, first of all we visit the root node, then we visit its left subtree, and then we visit its right subtree, and we keep on doing that until the nodes exist. So let's see that for this given example, what is going to be the path that we are going to follow. So first of all, we are going to visit the root node. So in this case, the first node we are visiting is going to be node number 5. then we are going to visit its left child. So left child in this case is 3. So again we are going to visit node number 3, and then again we are going to visit its left child, because remember it's root, left subtree and right subtree. So left subtree still exists over here, so we are going to visit node number 1. Now left subtree does not, nothing more exist in the left subtree, so now we will start visiting the right subtree. So we now will visit the node number 7. Now after visiting the node number 7, now there is nothing exist over here, so again we are going to go back to the root, because we still have to visit its right subtree. So when we start visiting the right subtree, again we are going to follow the formula for root, left and right. So root node in this case is going to be 8, so now we are going to visit node number 8. After that we are going to visit node number 6, and then we are going to visit node number 9, which is the right subtree, and this is going to be the traversal path that we are going to take. Now let's see that what would be the in-order traversal in the same manner. So again, as mentioned, the in order is also a DFS kind of traversal, but in this case the methodology we follow is that first of all we visit the left node, then we visit the root node, and then we visit the right node. So for this given example, what we are going to do is, first of all we are going to go to the left node all the way possible. So left node in this case is 1. So first node we are going to visit is going to be node number 1. Now for now we can't go left anywhere, so now we are going to visit its root node. So root node is in this case is going to be 3, and then we are going to visit its right node. So right node in this case is going to be 7. After doing that, after visiting all 3 nodes, now we don't have any more nodes to travel on the left subtree. So now we are going to visit the root node as mentioned over here, because we have already taken care of this left part. So now we are going to visit node number 5. Now again we still have values that we need to visit on the right subtree. So again we are going to take on the same initiative. So now the first thing we are going to visit is going to be the leftmost element for this right subtree. So leftmost element in this case is 6, so we are going to visit the node number 6 over here. After that we are going to visit the root node, which is 8, and then in the end we are going to visit the node 9 over here, which is this one. So this is how in order traversal works. So after understanding both the values and both the different traversal mechanism, let's see that what would be the optimal solution and how we are going to approach that. Okay, suppose this is the binary tree that we are given that we need to iterate over, and we are given the pre-order and in-order traversal for both of them. So in this case, the pre-order traversal for this tree is going to be, and the in-order traversal in this case is going to be. Now once we have both the values, let's see that what is the approach we are going to take. So if you closely observe both of these values for pre-order and in-order traversal, they both have something to offer. The thing they have to offer is that this pre-order allows us to determine that what the root of any section of the tree is, and this in-order allows us to determine that what is the left subtree and what is the right subtree of any given tree. How? Let me quickly show it to you. So if we see this pre-order traversal, the first value in this case is actually the root of the binary tree, which is 5 over here, which you can clearly see that the 5 is the root of the binary tree. So well, that is interesting information, but the thing is this alone is not helpful. If we see with this in order traversal for this 5, if we see the left side of this 5, there is only one entry over here, which is 3. And if we see in this tree, actually this 3 is the left subtree of this entire tree where the root is 5. Now if we see on the right side, the values are 6, 8 and 9, which is these 3 items, and this is actually the right subtree of this original given tree where the root value is 5. So now we actually have something meaningful that we can use. If we keep on repeating the same process, now for this pre-order traversal, again we see, okay, so the next value is 3. So 3 is already the left subtree. Now if we again break it from this in-order traversal, for this in-order traversal, we only have 3 value over here. We have nothing on the side, we have nothing on the right side, because the right side value is actually 5, which we have already identified that that is the root of this original value 3, which means we can determine over here that for this 3 it does not have any values on the left subchild and right subchild, because the very next value of this 3 is actually 5, which was already the root of this value 3. So now again we have some meaningful information. So far let's backtrack. The information we have found so far, that let me create an answer value over here where we have already found that the first value is 5, the leftmost value or the first left value or left subchild of this value number 5 is actually 3, and for this 3 it does not have any more children, so now we can add the values null over here. Okay, now we are done iterating up until this point, but we still have some more nodes that we need to iterate over. So based on this pre-order traversal, now the next node we have is 8. So now we know that the current root we are iterating over is actually 8. Okay, so we have this value 8. Now from this Inorder Traversal, we actually have these three values where this 8 is actually in the middle, because remember, this Inorder Traversal allows us to determine that what is the left subtree and right subtree of any given root. So in this case, if the root is 8, then the left subtree is going to be the value 6 and the right subtree is going to be the value number 9. So we are going to use it to our advantage. Now for this value number 6, again we are going to try to see that what is on the left of 6 and right of 6, but in this case, since we don't have any more information for this value number 6, the left value is 5, which was the original root which we have already iterated over, and this next value is 8, which was the root of immediate root of this value number 6, which we have already iterated over. So now we can determine that for this 6 we don't have any other value, so which means that we have two null values. So again, now let's, and same thing we can determine for this 9 as well, that for this 9 the leftmost value is actually 8 and in the right there is nothing over here, which means this 9 also does not have any more children. So now let's again backtrack based on the information we have found so far. So now on the right side, the value we got was 8, that was the root we iterated over, and we found that information based on the pre-order traversal. After finding this 8, now we started iterating over the left and right children of this 8. So left children was 6, so we iterated the value 6. Now the 6 did not had any more children, so we had the values null over here. And now then we had the value number 9, and 9 also did not have any more children, so now again we had the two more null values over here. And this is the actual binary tree that we were able to create based on this original given pre-order traversal and in-order traversal, and that is the solution that your interviewer is expecting, and that is what is needed for this problem as well. Now there are actually two ways to do this problem. There is an iterative way and there is a recursive way. If you know me, I love the recursive solution, so I'm going to opt for the recursive solution. Basically what we are going to do is, initially we are going to find the root value, and then we are going to find the left subtree and right subtree. Now again we are going to pick one value, so we are going to pick the left subtree. So now even for the left subtree we will have a root value and its left child and right child, and again we are going to keep on repeating the same process, and we will be continuing to building our answer, and same thing we are going to repeat for our right subtree as well. So basically we are taking a bigger problem and then dividing it into a bunch of different smaller problems. I know this looks really messy, but you get the idea of what I'm trying to convey over here. And let's see the time and space complexity in this problem. So time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over both in order and pre-order traversal, and originally it's going to be 2n traversal. The thing is, generically we can write it to big O of n. If we see space complexity, well, space complexity is also going to be big O of n, because recursively we might have to iterate over all the nodes, and it worst case scenario it could take big O of n space. This is a wonderful time and space complexity given that how complex this problem was, and based on the pre-order and in-order traversal we were actually able to build the solution for the binary tree. Now let's see the coding. So before we start coding, we will actually have to define that how we are going to use this pre-order and in-order array. Well, we are going to use this pre-order array to determine that what is the root value for any subsequent positions. And once we have the root value, we are actually going to use this in-order array to determine that what is the left subtree and right subtree for any given root. And once we have both the information, we are actually able to build our tree. Now the thing is, if you clearly understand that for this in-order array, we will have to look up at information in much broader fashion than compared to this pre-order array. So what we can do is, in order to iterate over this in order array, rather than iterating it just by considering this to be an array, we are actually going to create a hash map where we are going, which is going to allow us to iterate over this in order array pretty fast. And so let me define two global variables over here. First of all, once we have these two information, now from our main method, first of all we will have to iterate over this in order array, and then we will have to populate this in order index map that we just created. So let me quickly run a for loop. Now we have our hash map ready to go. Now we will have to create a separate method where we are going to call the recursion. So first of all, let me create a new public method. So now I have created a new method called array to tree that returns a tree node, and as an input I'm taking the pre-order array, the left portion and right portion, and now we are going to create this recursive method. Now before I do that, I will also have to initialize the values for this pre-order index and also for this in-order index map, so that I'm going to do it. Okay, now back to our recursive method. So for recursion, first of all, we will have to create a terminating case, and the terminating case in this case is going to be that if the value of left is greater than the value of right, if that is the case, we break out immediately and we will return null. If that is not the case, first of all, we will have to define our root value, and root value we are going to define from our pre-order array. So our root value is actually going to be the whatever this pre-order index value that we have, and then we are also going to increment the value of this pre-order index as well. So this is the root value, and after that we are going to increment the value of pre-order index. Now since we have our root value, we are actually going to create a new tree node called root, and for this root node we are going to assign the value that we received over here. Originally, the value of this pre-order index is 0, which means that the first value we are getting from this pre-order is the main root of the tree. Once we get that value, we will have to create the left subtree and right subtree. So we will have to call this array to tree method again, and we are going to populate the value for left and right child. So for the left child, we are again going to call this array to tree method. Inside the input, first of all, we are going to provide this pre-order array as we found as it is. Now for the left subtree, we are going to keep the value same for the left value, but for the right portion, the value is actually going to be different, and that is going to be different based on whatever this root value we had. So in this case, for the first value for this pre-order array, the root value is actually 3. So now for the left part, we already have the value, but for the right part, we are going to have to provide all the values that are present after this root node. So we are going to do that. So for that, now our in order index map is very helpful. Now we have both the information ready to us. Now we are going to call the right subtree in the same manner, but in this portion we are going to treat whatever the right variable we had already, but now we are going to change the left variable. So for the left variable, we are actually going to use whatever the value we had for the root value, and we are going to do it +1, and as the right limit, we are going to keep whatever the right limit we originally had. And after this recursion ends and after this function ends, we simply need to return the root variable. Okay, so now our recursive method is ready to go. Now all we will have to do is from our main method, we will have to call this recursive method that we just created. That should be it. So we are calling this pre-order method, but we are providing the pre-order array, and as the left position we are providing the value 0, as the rightmost position we are providing the value of whatever the pre-order length is -1, and that should do the trick. Now let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is pretty efficient compared to a lot of other solutions. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do Kth smallest element in binary search tree LeetCode problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Uber, Amazon, Microsoft, Facebook, LinkedIn, Apple, Google and Bloomberg. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary search tree, and we are also given an integer called k. Now we need to return kth smallest value from all the given values inside any given binary tree. So let's try to understand this with a couple of examples that are presented over here. So this is a binary search tree we are given, and if you notice the important property of binary search tree, where for whatever the root node, everything on the left subtree is less than that root node, and everything on the right subtree is greater than that root node that is present for this BST. So that is the definition of binary search tree. I'm just making it clear. And now for this example, this is the binary search tree we are given, and we are also given the value of k to be 1, which means we need to return first smallest value. So in this case, the first smallest value or the smallest value is going to be this value 1, and this is what we need to return as the output. Let's take one more example. So in this case, again, we are given a binary search tree, and we are also given the value of k is equal to 3, which means we need to return third smallest value. If we see in this case, this 1 is actually the first smallest value, same with this 2 is the second smallest value, and same with this 3 is actually the third smallest value. So in this case we will have to return this 3 as the answer. So I hope that you have understood the problem by now. Now let's see that what is going to be the optimal approach to solve this problem. Okay, suppose this is the binary search tree that we are given, and we are trying to find the kth smallest value at any given position. So the idea I'm suggesting is that for this particular binary search tree, if we make the sorted array of all the values and we sort them in increasing order, then whatever this array we have created that is already sorted, based on this it becomes pretty easy for us to find the kth value. How? All we have to do is just look up in this array and we will be able to find the value. Let me quickly show you what I mean. So for this particular binary search tree, if we see the sorted path where the first value is 1, then we have the value 3, then we have the value 4, and then we have 5, 8 and 9, and this is the sorted path that we have been able to generate. Now once we have this value, it becomes pretty easy for us to find any kth position. How? Suppose we are given k is equal to 2, we can immediately return second smallest value, which is the second value in this case, which is the value number 3. If we are given k is equal to 5, then we simply need to return this value number 8. If we are given k is equal to 3, we can simply return this value number 4. So now you get the idea that once we have this sorted path, it becomes pretty easy for us to find any kth position. So all we will have to work on is that from this given binary search tree, how can we actually create this sorted path? And if you know, or if you have followed my previous video, you know the answer. The answer is actually Inorder Traversal. So let me quickly show you the optimal solution using Inorder Traversal for this problem. Okay, so Inorder Traversal actually a depth first search kind of a traversal, which means that first of all, on the left side of the subtree, we go to the leftmost position, then we visit its node or its root value, and then we visit its right subtree, and we keep on repeating the same process. So let's see that what is going to be the path in this case. So path in this case is, first of all, we are going to visit the leftmost element, which is 1. So we'll visit node number 1, then we will visit node number 3, then we will visit node number 4 based on following this left node and right more formula. After that, we will visit the node again, which is 5, and then we will be on the right side of the subtree. So again, on the right side of the subtree, we will have to follow the same path, left node and right. But in this case, since this right side of the subtree does not have any left children, so we won't be able to update or traverse any left value, but we would be able to traverse the node value. So again, we will travel the value 8, and then in the end we would traverse the value number 9. So in this case, this is the path we are able to generate from this given input binary search tree using this Inorder Traversal. And if you see this path, this is actually increasing order, and this path is actually sorted, which is very good for us. So suppose we are given the k is equal to 3. So if kth value is 3, we can simply return 4 immediately. If we are given k is equal to 5, then again we can return this value number 8 immediately, as mentioned earlier. And this is the approach we'll have to take to solve this problem optimally. Now if you want to learn more about different kinds of tree traversal, check out my video over here. Now let's see the time and space complexity in this case. The time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree. And if we see space complexity, the space complexity is also going to be big O of n to accommodate our Inorder Traversal. There are actually two ways to solve this problem. One is the recursive way and second one is the iterative way. Now since you know me, I like the recursion better, and even in the coding, first of all, we are going to create our recursive method called Inorder, and that is going to return an array. So I have created the Inorder method that takes in a root value and also that takes in an array list. Now first of all, we are going to check the terminating case. So if the given root is equal to null, we can simply return whatever the array value we have. Okay, if that is not the case, first of all, we are going to call the Inorder function again, and we are actually going to call for the left subtree. So we are going to call with the root dot left child, and we are also going to pass in the value of whatever the array we already received. Once that is done, we are also going to add whatever the node value we have. So we are going to add the value for that particular root, and in the end we are also going to call the Inorder method again for the right side of the subtree, because remember, for the Inorder we are actually following the method of left node and right. So with this time we are going to pass in the value of the right child, and we are also going to pass in the value of the whatever the array we have created. Now once this method runs, simply we need to return this array list that we have been creating, Okay, now from the main method, first of all, we are going to create a new array list called nums. In order to populate this, we are actually going to call our inorder method, and we are going to pass in the value of the root, and we are also going to pass in the value of a new array list. Once that is done, all we will have to do is basically from this array list we simply have to return whatever the k minus 1th position element is, because remember this k is actually 1 index, meanwhile the array list we have been creating, that is 0 index. So that is one tricky thing that we will have to take care of. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. It is also very efficient in terms of space complexity as well, and I will be posting this in the comments so you can check it out the solution from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do validate binary search tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Bloomberg, Facebook, Uber, Google, Apple, ByteDance, Lyft, LinkedIn and Netflix. So that's why I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and one of the most liked tree problems on LeetCode. Basically, we are given the root of a binary tree and we need to determine that whether that given tree is a valid binary search tree or not. We are also given the definition that what a valid binary search tree is. Basically, for any given tree, if this root value or the node value, so if this is the value of the node, basically every single value that is present on the left of the node should be less than whatever this node value is, and every single value that is on the right side of the node should be greater than whatever this node value is. So if that is the case and that is true for the entire given tree, we can define it as a valid binary search tree. So let's take a couple of examples that are shown over here. So in the first example, well, basically the node value we have is 2. So in the left subtree we only have one value, that is 1, which is less than this 2, and on the right subtree we only have one value again, which is 3, which is greater than this node value 2. So in this case we can consider this to be a valid binary search tree, and in this case we will return true. But if we take a look at the second example, so in the second example we are given this root value as 5. So this value, node value is 5, that is okay. If we see on the left subtree we only have one child and that is the value is 1. So this is again less than whatever the value we have for the node value. Now if we see on the right subtree, the value of this is actually 4. So 4 is again less than 5. So because this 4 is less than 5, and remember that we have the definition of valid binary search tree that everything on the right subtree should be greater than whatever the node's value is. So in this case, this value is actually not greater than the value of this root node. So in this case, this is not an valid tree. So in this case, we will return false. And this is what we have to define basically. Now, based on the definition, we can define that what a valid binary search tree is. That for any particular given node, if its entire left subtree, if that is less than that node, and if its entire right subtree, if that is greater than that node, we can define that to be a valid binary search tree. Well, if that is the case, the first intuition that comes to our mind is that for any given node value, what we can do is we can check its left child and right child. If the left child is less than it and right child is greater than it, if that is the case, we will keep on repeating the same process for all the subsequent left child and right child with its root node, and in the end, if we reach to the end of this tree, we can return true immediately, saying that this is a valid binary search tree. Well, let's try to apply that same logic for this particular example. Basically, we are given this node 5. So this 3 is actually less than 5 and 8 is actually greater than 5. So in this case, this portion is actually valid. Now again, for this 3, this 1 is less than it and 4 is greater than it. Again, this portion is also valid, and same is true for this 8, 6 and 9 as well. So in this case, we can define this to be a valid binary search tree, and we can return true in this case, saying that this is a valid binary search tree. But the thing is, this solution is not the most optimal way to solve this problem, and let me quickly show you why. Because based on the same logic for this 5, this 3 and 8, again, okay, this is less than, this is greater than, so far this is valid. Again, for this 3, this is 1 and 4, so this is less than, greater than, again this is valid. But now for this 8, this is also 2 and 9, so this is less than, greater than, again this is valid. So all three portions are valid. By definition, we would treat this to be a valid binary search tree, and that would actually be a false positive. Why? Because remember that by the definition for this node, everything that is on the right side of this tree should actually be greater than this node 5, but in this case this 2 is actually less than this 5, and because of that particular case we will need to return false in this case. The thing is, based on our previous method we would have returned true. So let's see that what would be the actual optimal solution to solve this problem. So the idea for the optimal solution in this case is that we are actually going to do Inorder Traversal on the given binary tree to determine that whether it's a valid binary search tree or not. Well, if you want to learn more about different types of tree traversals, you can check out the video over here. Now let's get back to the question at the hand. So basically what the idea I'm suggesting is that if we do Inorder Traversal in any given tree, basically the idea for Inorder Traversal is that first of all we visit the left subtree, then we visit the node, and then we visit the right subtree. Also, this Inorder Traversal is a depth first search kind of a traversal where we are actually going in the depth first and then we are visiting the different nodes. So in this case, the traversal that we are going to do is that first of all we are going to do go for the left subtree. So for this node, left node exists. Again for this node, left node exists. So first of all we are going to visit this left child. Then this child does not have any more children of its own. So now we are going to visit its node. So we are going to visit this node 3, and then again we are going to visit its right child, which is 4 in this case. After doing that, we are going to visit the node, and then we will keep on repeating the same process. So let's see that what is the path we are going to take for this Inorder Traversal. Well, for this problem, basically the path we are going to take is that first of all, as mentioned, we are going to visit this node number 1. So first node is going to be 1, then we are going to visit node number 3, and then we are going to visit node number 4 in the fashion of left node, and then right sub node. Then we are going to visit the node. So we are going to visit node number 5. Now we are start going to keep on iterating on the right subtree. So even on the right subtree, again we are going to follow this method of left node and right. So for this left subtree, now this becomes the root node or the node, and this also has a left subtree existing. So first of all we are going to visit this node number 6, then we are going to visit node number 8, and in the end we are going to visit this node number 9. So this is the Inorder Traversal for this given binary tree. Now the thing is, if you see this traversal, basically everything is going in increasing order, and this whole thing is actually sorted. And this is the property of this Inorder Traversal that we are going to make use of, and we are going to solve it optimally. The idea is for any given tree that we are presented with, we are going to do an Inorder Traversal, and during the Inorder Traversal, basically the only thing we have to keep track of that any given node that we are iterating, whether that node is actually greater than its previous node or not. If it is not greater than its previous node, immediately we can return false. So in this case, because this was a valid binary search tree, we were able to get an Inorder Traversal that is completely in increasing order, and all the previous nodes, they are actually less in value compared to its next subsequent node, and this property is maintained throughout the entire journey. Now let's see one example where this is not the case. So in this example, we can clearly see that this node 2 is at the correct place, and this is not a valid binary search tree. So let's see the Inorder Traversal over here. So in this case, the path is going to be, the next node we are going to visit is actually 2, and if we compare this node 2 to its previous value, the previous value is actually 5. 5 is actually greater than this 2, which should not be the case, and immediately at this point only we can conclude that this is an invalid binary search tree. We will return false immediately in this case, and that is the answer we are going to use. Now actually there are two ways to do Inorder Traversal for any given binary search tree. There is an iterative way and there is a recursive way. If you know me, I like the recursion better, so I'm going to show you the recursive way in the coding, but it can be also done iteratively as well. And the tricky part in this problem is to identify that we need to solve this problem using Inorder Traversal. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present. For the space complexity, we are using recursion, and we might have to store n characters in the worst case scenario. First of all, we are actually going to define a global variable called previous to store the value of the previous element. Now let me create a new Inorder method that would be our recursive method. So now I have created a new Inorder method that returns a Boolean answer, and we are taking just a root value as the input. Now first of all, we are going to create the terminating case that if the given root is equal to null, we are going to return true. If that is not the case, first of all, for the Inorder Traversal, we will have to call the leftmost function or leftmost value. So we are going to do that. So first of all, we are going to see that if the answer for the root dot left, if that is false, we will return false. If that is not the case, we will move on towards our next condition. Okay, so if we did not return false from our left side subtree traversal, then we are going to check our condition. So the condition we are going to check is that whether the current root value, if that is less than or equal to the previous value, if that is the case, which means that we have actually found an invalid binary search tree, so we can return false immediately. So if we don't return false by this point, which means the previous value was actually less than whatever the current root value we had, which is a good sign. So now what we are going to do is we are going to update the value of our previous variable. So that is going to be the current root value. And then after that, we are going to call the right side subtree as well. So we can simply return the in order for the right subtree. Now from our main method, all we will have to do is we will have to set up the value of the previous character. So initial value is going to be the null, and then we are going to call this in order method. Okay, seems like our solution is working as expected. Let's submit this code. And our submission runs pretty efficiently compared to a lot of other solutions, and that is because the code runs in 0 milliseconds. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do lowest common ancestor of a binary search tree lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Facebook, Amazon, Apple, Google, Microsoft, Uber, Reddit, and Twitter. So that's why I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode easy problem, and basically first of all we are given the definition that what a lowest common ancestor means. The lowest common ancestor is defined between any two nodes P and Q, such as that the lowest node in given tree that has both P and Q as the descendants, where we allow a node to be a descendant of itself as well. We are given a binary search tree, and we are also given two nodes in that binary search tree, and now we need to find the lowest common ancestor between those given two nodes. So let's try to understand this with this example. Basically we are given a binary search tree over here, and we are also given the value of P and Q to be 2 and 8. So subsequently, if we see over here, 2 is located at this place and 8 is located at this place. So the most common element, or the immediate common element that we can find, is actually 6 in this case. So that's why in this case we are going to return 6 as the answer, because that is the lowest common ancestor between the node 2 and 8. If we take one more example in this case, so over here we are given this P is equal to 2 and Q is equal to 4. So P is located at this 2 and Q is actually located at this 4. Now if you see in this case, actually this 4 is a descendant of this 2. So that's a given fact. But we are, remember, we are also told that we allow a node to be a descendant of itself as well. So in this case, since this 2 and 4, so 4 is already a descendant of this 2 and 2 is already a descendant of its self. So in this case, we will have to return this 2 as the answer. And that is what is given over here. We are given one more example where we are given only two nodes for this given binary tree. So the binary tree looks like this, 2 and 1. And in this case, we are given the value of this P to be 2 and Q to be 1. So again, we can see that in this case, this 2 is already a descendant of itself and this 1 is actually a child of 2. So because of that, 1 is also a descendant of this 2. So in this case, we will again return this 2 to be answer. Now, I hope that this makes understanding the problem more easier. And now let's see that what is the approach we are going to solve this problem. Okay, first of all, I'm actually going to show you a bunch of different binary search trees, and for all of those binary search trees, I have created some P and Q values, and we are going to see that what was the lowest common ancestor and why that was the lowest common ancestor, right? Now, we already know that important property of binary search tree, and that is that for any given root value, everything on the left subtree of that binary search tree is actually less than that, and everything on the right side of that binary search tree is greater than that. We already know this important property, and we are going to take it to our advantage based on this given root value or any root value and with subsequent P and Q values. So if we see over here, in this case, the given value of P is actually 6. And if we start traversing through this binary search tree, immediately we would find the 6 to be present over here. So because we find the 6 to be present, there can only be one possibility, that this Q or whatever the value of q, that would either be on the left side of the subtree or right side of the subtree. But we already find the value to be 6 over here. So immediately we can return 6 to be the lowest common ancestor, because anyways this value of q is somewhere supposed to fall inside the remaining binary search tree, and in this case it is on the right side of the subtree. So we will return 6 as the answer. This makes sense, right? Now the next example, again we are given the same thing. We are given this value p to be 11 and q to be 9. So we know that this p is over here and q is over here. 11 is going to be answer, but let's go ahead with our algorithm. So first of all, we'll start iterating over this root. So the root value is actually 8. Now for this root value, we are going to compare it with the values of p and q, right? In this case, the value of p and q both are actually greater than this 8. So because both are greater than this 8, we know based on the property of binary search tree that they are meant to fall somewhere on the right side of this given binary search tree. So we will start iterating over the right side of the binary search tree to either find the values of p or q, or if we can't find, we will try to find the lowest common ancestor. So when we start iterating over on the right side of the subtree, we will ignore this left side of the subtree. We don't care. Now this value is 11. This value is 11 is actually matches the value of this given p. So immediately whenever we find a match with either p or q, we can return that to be the lowest common ancestor immediately, and in this case this is going to be the answer, because this 9 is meant to be somewhere below this binary search tree, and in this case it is immediately right here present. So we will return this 11 to be the answer, which is the lowest common ancestor. Let's take one more example which is very similar. So in this case this value is p is equal to 3 and q is equal to 1. Now again, based on our algorithm, we will start traversing over this binary search tree. Now the first value we traverse, whenever we compare its value with this p and q, immediately we find a match with this p to be over here. So because we find a match over here, do we really need to iterate over this given binary search tree? Well, the answer is no. Why? Because we know that this q value is somewhere going to be down below, and that is always going to be this descendant of this p. So again, we are going to return the values 3 as the lowest common ancestor. So far it makes sense that whenever either we identify the value of p and q, we can return that to be the lowest common ancestor immediately. But what happens if the case is a little bit different? So in this case, I have given the value of p to be 6 and q to be 9, right? Again, let's start with our algorithm. So we'll start iterating over this binary search tree. So first of all, this value is actually 5. So because this value is 5, we'll try to see that, okay, we will compare it with this value of p and q, right? So actually this 5 is less than p and less than q. Both p and q are greater than this root value. So immediately it is meant to fall somewhere on the right side of the subtree. So now we'll start iterating on the right side of the subtree. We'll ignore these two because we don't need them. Now again, this value is 7. So let's compare this 7 with this value of p and q. Well, if we compare this 7 is actually greater than this p, and this 7 is actually less than this q, right? So we can conclude this 7 actually falls somewhere in the middle, because for the 7 on one side 6 is meant to be, because 6 is less than 7, and somewhere on the other side 9 is meant to be, because 9 is greater than the 7 based on the property of a binary search tree. And if we utilize that to our maximum advantage, we can immediately determine that this 7 is the common point between this 6 and 9, where on one side 6 resides. So 6 resides on the left side over here, and 9 resides on the right side of the subtree. So on the right side of the subtree, this is where 9 resides. So we'll return 7 to be the answer in this case. And this is the approach we are going to follow. So every single time for any given tree, we will start iterating over that tree, and we are going to compare its value with p and q. Based on that, we will decide that whether we go on the left side of the subtree or right side of the subtree. The moment we find a match between p and q, whatever the value we found, if we find that, we will return that to be the lowest common ancestor. If we don't find a match, and if we are in a situation where this value of p is on the left side of this any root value and q is on the right side of any root value, then immediately we can return that value to be the answer. And this is the approach we are going to take to solve this problem, and this is the optimal way to solve it. Now there are two ways to solve this problem. We can either solve it recursively or we can solve it iteratively. Now I like recursion better, but iterative method will also work as expected in this case. Now for the recursion, if we see the time and space complexity, the time complexity is actually going to be big O of n, because we will have to iterate over all the values in the worst case scenario. And for the space complexity is actually going to be big O of n as well, will, because we will have to maintain the runtime stack for this recursion method. Well, one good thing in iterative method is that for iterative method the time complexity is still going to be big O of n, but for the space complexity we can actually use a constant space complexity for the iterative approach. But in the coding, because I'm trying to improve my recursion, I will be showing you the recursive method, but just remember that iterative approach would be the better option in this case. So we are going to use the same method as our recursive method, and first of all, in this method as an input we are given this root value, we are given the value of p and q. So first of all, because we don't need to deal with this tree node, we will actually have to deal with this integer value. So I'm going to initialize three variables called the parent value, p value and q value, and I'm going to assign the values based on this whatever the input we get. Now we will have to check that whether this parent value, if that is the common point between p and q, or either p and q falls on one side or other side of this binary tree. If that is the case, we will call our recursive method again. So first of all, we are going to check that if this p value and q value both are greater than this parent value. If that is the case, which means we will have to iterate on the right side of the subtree. So we are going to call the iterative method on the right side of the subtree. If that is not the case, we are going to check that whether this p value and q value both falls on the left side of this parent value. So again, we are going to do that. So if both p value and q value are less than the parent value, which means we will have to search the left side of the subtree. So we are going to do that. Okay, if that is not the case, which means that whatever this root value we are at, that is either p or q value, which means we can return root immediately. That's it. That should be working. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions in terms of time complexity. I already mentioned you that for the space complexity, this recursive solution is not the most optimal, but I want to practice recursion, so that's why I did that. You can find an iterative solution that works as well. And I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today actually we are going to learn about a new data structure, and we are actually going to learn to implement a trie or a prefix tree. And if we see some of the companies where I want to get a job, who already asked this question, there are companies like Amazon, Google, Twitter, Microsoft, Oracle, Apple, Facebook, Goldman Sachs, Uber and Bloomberg. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are going to implement a trie over here or a prefix tree. So first of all, in the problem statement we are given the definition that what a trie is, and actually I'm going to show you very eloquently that what a trie is and how it works. But let's understand the definition first. Basically a trie is a prefix tree, which is a tree data structure that is used to efficiently store and retrieve keys in a data set of strings. There are a bunch of different applications of this trie data structure, and I'm going to go over all the applications soon as well. Now, if we see that what is needed in this problem, basically we need to initialize a trie object first of all. Then we need to create three different methods which are mentioned over here. So first method is the insert method, which does not return anything, and basically we are only given the input as a string word, and we need to insert this word inside this new trie object that we are initializing. After doing that, we could be given a search method where again as an input we are given a string called word, and we need to return true or false, which means that whether if this word exists inside this trie object that we have created, we need to return true, otherwise we need to return false. And there is also one more method where again we are returning true or false, and the name of method is starts with, where we are actually given a string and the name of the string is prefix. But basically we need to check that whether this prefix actually exists as a part of any existing word inside this trie object, and if that is the case we need to return true. If that is not the case, we need to return false. So here is an example that we are given. So suppose we are given as an input where actually first of all we are creating the trie, we are inserting some word, we are searching for some words, we are doing the start with operation, and this is the explanation. So basically we initialize the trie object as mentioned. Then first of all we insert the word apple. So okay, so currently apple exists over here. Now again we search for that whether apple exists or not, and because it exists we return true as the answer. Again we search for with the word app, but the thing is, remember, so far we have only inserted the word apple. App does not exist as a whole word, so that's why we return false. Again we search for starts with method for this word app, and remember, because this app is actually a prefix of this apple, so we return true in this case, and so on and so forth. We can do bunch of different operations. So this is what is needed. Now let's understand what a trie is. Okay, so first of all, let's try to understand that what a trie actually is. Basically, a trie is a tree-like data structure, but it's a little bit different and a different variant of a tree. Now, if we know for any single tree, the basic properties are that every single tree has a root node. Now, this root node has some subsequent children nodes. There could be n number of different children, and those children can have some children of their own, and their links actually found some meaningful relationship. So that is what we are going to use to generate this trie, but we are actually going to generate this trie to store different string values per character. That is the important property, per character. So it makes us easier to understand or find different words or different strings, and there are n number of applications of a trie. Let's try to understand trie with some example. So first of all, as any different tree, we are actually going to have a root node, right? Now suppose for this root node, what we are trying to do is we are trying to add some different string value. So let's take a string value. Suppose the first string we are trying to add is actually the word fang. So if we take this word fang, first of all we will have to add the word f, because remember I already told you we are going to do it character by character. Then we will add a, n and g. We are going to add it in this sequence. So in order to do that, logically speaking, for this root is going to remain common. But the thing is, first word we will have to add is fan. But the thing is, first we will check that whether is there any children of this root node which is actually f. If that is the case, we are actually going to leverage that. But this does not have any children. So if this does not have any children, we are actually going to create a new children f. Now again, with this f there is no children, that is a. So again we are going to create a new children, then again we are going to create a new children, and then we are going to add the values of n and g as well. After adding this, we have actually created a root inside this trie data structure which represents this word fang that we were originally trying to create. After creating that, we will have to find some way to identify that this fang word has actually ended. So what we are going to do is we are actually going to create a special character or a special node over here which we are going to denote as an end node, which defines that the word has actually ended over here, right? After doing that, let's try to add one more word. So suppose rather than fang, we are trying to add the character mang. So let's try to again add mang over here. Now for this mang, first of all we are going to check that whether this m exists as one of the children of this root node. So m is also no children, so first of all we are going to add m, and then we are going to add subsequent characters, and we are going to link them with this path. After that, in the end, we are actually going to add a special character and denote that the word has actually ended over here. So let's do a quick recap. Basically what we have done so far is we have actually created two separate branches where if we go depth first search diving in those branches, we would actually find those subsequent words in those particular branches. So it makes pretty efficient for us to identify any string and to see that whether it exists or not, and predict that what the person is going to copy. Now suppose I'm trying to add the next word fan. Now for the adding this next word fan, what we are going to do is first of all we are going to check f exists or not. So f exists over here. So because f exists, we are actually going to leverage that. So now we are not going to add any entry over here. Again, this a also exists as one of the children of f. So again, we are not going to add any entry over here. Now this n. So n is not a children of this original a. So we are actually going to create an entry over here. So we will create an entry over here. And we are actually going to name it as n. And now since this word ends over here, we are actually going to create this end node over here. So again, remember, if we go depth first search in this direction, we will actually be able to find this word fan, and that is the whole purpose of a trie. Now let's try to add one more word which is man. Sorry, maa, ma. So if we try to add this word ma, so first m also exists over here, a also exists, and a also exists. So because these three exist, we are actually not going to break this link and create this end word over here, or we are not going to do that. Actually, we are going to keep this as it is, because this MAA is actually a prefix of this original word mang that we have already added to our trie, and that is why a trie is also called a prefix tree. So now the word makes sense that why a trie is called a prefix tree. And basically this is what we are trying to implement. There are a bunch of different applications of a trie, and let's see some of the applications that are really cool in real life world. So before we start implementing the method, first of all, let's understand that what are different applications of a trie. So applications like autocomplete, where you type something and it automatically gets completed or understood by that particular product, that is implemented using trie. So features like Google Chrome, Amazon, where you type few words and then it automatically understands that what you are trying to do and automatically gives you the answer, that is implemented using that. All the spell checks or all the dictionary related mechanisms, they are also implemented using some versioning of a trie. Games like word search, word puzzle, wordle, they are also implemented using a versioning of a trie. And features like predictive text search or expected text search, that you type something, it automatically expects that what could be the next potential words. You see that in YouTube, Google all the time. They are also implemented using tries. So these are only few but very powerful applications of a trie, and there are hundreds of them. I haven't mentioned them. So that's why trie is important to understand. Now let's move back to our question and start implementing those three methods. So first method they are asking us to implement is an insert method, where we are not returning anything, but we are inserting different strings into our trie. So for this example, we are actually going to implement these four different types of strings into our trie, and we will see that what would be the logic behind it. Now, as mentioned earlier, that every trie actually has a root node. So again, with our trie, we are also going to have a root node. Now from this root node, the idea we are going to use is that whatever string we are trying to insert, first of all, we will check that whether the first word that we are trying to implement or the first character we are trying to implement, if that is present as one of the children of the existing root node or not. If it is children of that particular root node, we would keep on branching for that particular child and keep on updating the number of characters that we are trying to implement. If it does not exist, we will actually create a new node or a new branch, and we will add that entire word into that branch. Now, as mentioned earlier, the moment we reach to the end of that particular node, we will actually have to create an end node to denote that this word actually ends over here. So let's start implementing what is being asked over here. So first we are trying to implement the word apple. So A does not exist as any of the children of this root node. Currently it has no children, so we will have to create a new node. So first we are going to create a new node for apple. Okay, so let me create a new node A, and then I will keep on appending all the remaining characters. And after adding all the word, because this word ends at this E, I am actually going to create a special node, and I am going to denote it as an end node. So that is to for us to understand that this word actually ends over here and we don't need to move any further. Okay, now next word we are trying to implement is G. And also remember one thing, I forgot to tell you that this root can have potential 26 different children, right? And this 26 different children can have 26 different children of their own. So the mechanism we are going to implement to find that whether a node contains any particular children or not is actually going to be used based on some key value mechanism. And because it's a key value mechanism, the whole operation of searching that whether any node or anything, if that is part of any children of that particular node or not, that is being done in constant time, so that it helps us understand, helps us to maintain the consistency and speed of our data structure. Now let's move back to adding the word Google to our trie. So for the word Google, we do not have any children that is starts with G. So we are also going to create a new node over here or new branch over here, where first character is G, and then we will add all the remaining characters. As previously mentioned, at the end of the word we are going to create an end node. Okay, now things become a little bit interesting with this word Amazon. So for this word Amazon, when we start checking that whether this A is a children of this root node or not, we find that A is already a children. So we will keep on updating the value over here, that okay, we have already find a word or a character that is already a children, and then we will keep on moving to the next character. So first this A is already present, so we ignore that. Now next character we want to find is M. So for this M, we will try to see that whether this A contains any children that starts with M. But the thing is, currently this A only contains one children that starts with P and not M. So we will have to create a new branch over here. So let's create a new branch. So new branch starts with M, and then we will add all the remaining word characters over here. Okay, and now the next word we are trying to implement is amazing. For the amazing, okay, we already have a children of this root that starts with A, so we have taken care of this. M is also present as one of the children. Okay, now A is also present as one of the children of this M. Okay, so that is also good. Now this Z is also present over here. Now for this I is actually not present as one of the children of this Z. So we will actually create a new branch over here that starts with I, and then we will add this N and G over here, and in the end we will create, or we will add the end node over here. And now we have actually inserted these four characters as, or these four strings, into our trie. And if you see, we can find each one of them by going in DFS motion in any particular branch. So first of all, this gives us the value Google, this gives us Apple, this gives us amazing, Amazon, and this gives us amazing. So that is how tries typically work. Now let's move on to the next method that is being asked. So for this search method for our try, we will be actually given a word as the input, and we will have to check that if that word exists inside our given try, we will have to return true. If it does not exist, we will have to return false. So let's start implementing the same method, and actually we are going to use the same try that we have created. Okay, so let's use the same try that we have created earlier, and we will try to see that whether these four strings do they exist inside this given try or not. So let's understand the logic behind it. Well, if the string exists, basically all we will have to do is, first of all, we will check that, okay, whether the first character, if that is the one of the children of this root node or not. If that is the children, we would keep on checking its children for this next subsequent words and try to complete this entire word. If we are able to complete this entire word without this try breaking or not able to find the children, if we reach to the end, we can conclude that this word exists. If we cannot come to the end, we will conclude that this node does not exist. So first of all, let's try to see in this example. So for the first word is A. So A exists over here as one of the children. So we will ignore this one. Now next word is M. M also exists, so we will again ignore this one. The next one is A, again this word exists. Now Z, I, N, G, they all exist in this particular fashion. So this word amazing exists inside this given try. So because it exists, we will return true as the answer in this case, right? Now let's try to search for this word good. Now for this word good, the first character is G. So first character is G present over here. So okay, we are good up until this point. Next character is O. O is also present. Again, O is also present. So we can ignore first three characters of this good. Now for this next O, we do not have a children that starts with value D. So because of that, we do not have any new branch over here that starts with D. So we can actually conclude that the word good does not exist in this case, and because it does not exist, we will return false over here. Okay, now let's try to search for the word Googler. So again, for this word Googler, okay, G also exists, O exists, O exists, G exists, L exists, and E exists. Okay, up until this point, all the words exist. But when we try to search for the next word, we actually encounter that, okay, this is the end node of our try or of our DFS search for this particular direction. So because it is the end word, we will actually return false over here, because this word has not been completely searched, because it does not exist inside our try, and we are actually able to do it pretty quickly and pretty efficiently. Okay, so now next word is app. So let's try to see that whether this word app exists inside our try or not. So first of all, we check for this word A. A exists over here. Then this word P. P also exists and P also exists, right? So we are up good up until this point, and our mind will say that, okay, because this word exists, we need to return true. But the thing is, that is not the case. The idea we are trying to do in this search method is that we are trying to see that whether the whole word that is given as the input exists as only a word inside this given try. But for this app, if we try to see the next node is actually the SL and E. So there are still some characters that exist inside this given DFS path that we are traversing, and the next node is actually not the end node. So because the next node is not the end node and there are still some more nodes that exist, this app is actually a prefix of original word apple, but not the whole word as it is. So that's why in this case we need to return false as well. And this is the important thing that is differentiating between this method, search method, and the next method we are going to implement. Now if we see the time and space complexity, in this case the time complexity for this method is actually going to be big O of n, where n is the number of characters that are present that we are trying to search in any given word. If we see space complexity, for the space complexity we are actually not using any additional space, so that is going to be the constant space complexity for this case, which is pretty efficient in my opinion. So now let's understand our starts with method, and we are also going to use the same try that we have created before, right? And we are going to see that whether the words that starts with these characters, are they present inside our given try or not. So again, this is very similar to the search method, where we are going to iterate over word by word or character by character for any given word, and we will see that whether that is present inside our try or not. If that is present, we can return true. If that is not present, we will return false. So let's see that in action. So first of all, we have this character a. So a is already one of the children of this root node. So okay, we are good up until this point. Then we have m is also a children over here, and then we have a. So a is also a children of this one. So we can conclude that because this word ended, we do not have any more things to search for, and all of the characters, they were present inside this given try. We would actually return true. In this case, they are saying that the word that starts with ama is actually present as one of the children or one of the branches of this try. Now let's try to search for this word apk. So a exists and p exists, but the thing is, for this p we do not have any children that starts with k. So because of that, this k is not present. We can actually return false in this case, saying that we do not have a word that starts with apk as the prefix inside our try. And remember, because we are searching through prefix, that is why this is also called prefix tree. So yeah, mind blown, right? Mine as well. Now let's try to search the word good. Well, there is Google, but there is not good. But the thing is, Google is pretty good. Yeah, so that's why it's one of my dream companies. But let's try to search that. So okay, this is GOO. So GOO is present over here, but this D is not present as one of the children of this O. So because of that, we will also return false in this case. Okay, now we have this word apple. So apple is actually the entire word that is present over here. And if you look at it, we do have a word that starts with the word apple, even though it ends at apple. But the thing is, also it starts with apple, right? So, and the name of the method is actually starts with. So why should not we return true in this case? So this will also become true, that okay, word that starts with apple is present inside our given try. And that is the logic we are going to use to implement the starts with method. Again, very similar to the search method, just a little bit different variations. Now if we try to see the time and space complexity, in this case the time complexity is also going to be big O of n. That is where n is the number of characters that are presented inside any word that we are trying to search. If we see space complexity, the space complexity is also going to be big O of 1, or constant space complexity, because we are not storing anything in our text stack. This problem is asking us to implement insert, search, and starts with method. But before implementing these three methods, first of all, we'll have to define that what a try node is. This is only a try class. So I would be creating a separate class called try node. Now in this try node class, first of all, let's go over some basic methods that we are going to use that will enable us to do a lot of things. First of all, we have defined a finite number of cases R, which is 26, because any single node can only have up to 26 distinct children, because each children represents a character inside the alphabet. Now every single try node has a certain set of links, and links are defined by the children of that particular node. We also created some more methods, so let's go over them. So one method is contains key method, where we pass in a character and we get the answer that whether any particular link or any particular node does that contain that particular character as one of its children or not. And we can get the answer in a constant time complexity, because remember, we are using array indexing, and the maximum possibility of indexing can be 26, and we can get the answer immediately. Same, we have a method get, where we provide the character and we get the answer that whatever the value of that particular character is inside any of the children of any try node. We also have a method put, where we provide the value of a character and the node we are trying to put it as, And we also have set and is end method. That is to define that whenever we run out of words that we need to put in any single try block or any single try branch, the last node is going to be is end node, and we will mark its value to be true. So now let's start implementing the try node. So first of all, we will have to create a try node root. So let's do that. Now since we have our root node, first of all, for this public try method, we are going to initialize the root. After doing that, first of all, let's start working on our insert method. So for our insert method, we are going to have a root node. Now we are going to iterate over the given input word. We will define that what is the current character we are at. Now first of all, we will have to check that whether the given node we have, if that contains that particular key or not. So if the given node does not contain that key, we will actually have to create a new entry over here. So we will use our node.put method, and inside that we are going to pass in the value of the current character, and we are going to create a new try node for that, and then we are going to update the node's value. And once this loop ends, basically the last node we are at, we will have to set its value to be the end node. So we are going to mark its value to be the set end value, and which would basically, so it defines that this is the last node. Before we work on the search and starts with method, remember both search and starts with method, they are pretty similar to each other. So we are actually going to create a supporting method called search prefix. Once again, we are going to initialize the node to be the root node, and now we are going to iterate over the given word. So now we are going to check that if the current node, does it contains the given character or not. If it contains the given character, we can actually set the value of node. If it is not present, we simply need to return null, and that's it. And if we somehow reach to the end of this loop, we can simply return whatever the node we are at. Now from this our search method, basically what we are going to do is, first of all, we are going to initialize our try node, and we are going to pass in the value of the word. Now we simply have to return that whether the current node we get in the return, and if it is not null and it is end, we can simply return true. And same thing we are going to do for our starts with method. So again, for our starts with method, we are again going to call the search prefix method, and basically all we will have to check that whatever the return value we get, if that is not equal to null, if that is not equal to null, we can simply return true, and that should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to a lot of other solutions. And it is also very much efficient in terms of space complexity. The thing is, I was not able to come up with this solution on my own. I actually had to use a lot from the solution tab, so I just want to make it clear. So yeah, everyone has to go through it, and I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do design, add and search words data structure lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Google, Microsoft, Apple, Facebook, ByteDance, Twitter, Uber and Lyft. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and as the name suggests that we are actually designing a data structure where for this data structure we have to support that we can add new words to this data structure, and if given any string, we can actually find the previously added words or strings as well. So we are being asked to implement the word dictionary class. Now in the word dictionary class, first of all, we'll need to initialize the word dictionary object, and then we need to create two different methods. First method is add word method that takes in a string word as an input, which being done, it adds the word to our data structure that we can use to match it later. And then there is a boolean method called search, where again we provide a string word as an input, and that returns true or false if that word has been previously added or not. We are also given one more condition, that for the search method there could be dots, provided as inputs, where we can conclude dot to be any letter. So if we are given the word something like bad, that is already being added, and then we are asked to search for the word using b dot d, actually these two words we can consider same, because this dot we can consider it to be a. So let's try to understand this with an example. Over here we are given a bunch of different add word and search word mechanisms, and this is the explanation provided. So basically, first of all, we initialize the object word dictionary. Now for that, first we add the word bad, dad, mad. We add all these three words. Now first of all, we search using pad. So pad is not present, so we return false. Then bad is present because we have previously added it. Then we are also given a word which is dot ad. So this dot can actually mean anything, and if we see, we already have a word like bad and dad, that both, and even mad, that all three of them, they actually match with this string, so we can return true in this case as well. And we are also given one more search criteria, where we are only given b dot dot, which means for these two dots we can conclude any other word, and since we already have a word bad added, we can conclude these two to be similar, and we need to return true in this case. So before we start the solution, first let's understand that what a trie is. If you want to check the full explanation, you can check out my previous video over here. Now let's move back over here. So basically, a trie is actually a form of a tree, whereas any given tree, it has a root node. Now this root node can have many subsequent children, and each children can have some children of their own, and based on that, we actually use trie to search, store, and iterate over different strings. And for any given strings, we actually use it character by character to store distinct values inside this given trie, and based on per character, we actually store it in a manner where it becomes pretty fast for us to find that whether any particular parent node contains some character as one of its children or not, and then we iterate in some particular fashion, in DFS fashion, to find any words. So suppose these four are the strings we are trying to add. So let's initialize our trie data structure. So first of all, we are actually going to have a root variable. Now for this root variable, we are going to store all of these values one by one. So first let's store the value hello. As mentioned, that for any given string, we are actually going to go character by character. So first of all, we are going to take the character h, and we are going to see that does this root node has a child that is actually starts with h. It does not. So we are actually going to create a new node over here, and this node starts with h. Now we are going to add all the values of subsequent characters because they don't exist. So I'm going to add append e, l, l, o. And after adding all of these values, actually we are going to have an end variable that denotes that this word has actually ended over here. So far, if we iterate in this direction in this given trie, we can actually form the word hello, and when we reach to this o, we will actually encounter a special node that denotes that this is actually the end node, and if that, whenever we identify that, we can conclude the word has actually ended. Now let's add this word hi. So if we want to add word hi, basically first of all we will check that whether this h exists or not. So h already exists as one of the children of this root, so we do not need to create a separate branch for this one. But the thing is, for this particular h, I does not exist as one of its children, so we are actually going to create a new branch over here, I, and we are going to denote that this represents this word h, and then because this word ends over here, we are actually going to denote an end node over here. Let's add one more word, that is pop. So if we want to add pop, again p does not exist, so we are going to add, or we are going to create a new branch, and we are going to add all of these values, and we are going to add the end node. Now this next word is pond. So again we are going to use the same methodology. So p and o exist as the children, so first two characters we are done with. Now from here we will have to create a new branch, so we will do that, and after that we will add our end branch, and this is the logic we are going to use to implement our insert or add method to add different strings inside our word implement data structure. And this is the logic we are going to use, that first of all we are going to check that any character exists as the children of the root or not. If it exists, we are going to leverage that particular branch. If it does not exist, we are going to create a new branch, and then we will keep on making separations, and based on that things becomes pretty easy for us to find different words. Okay, so for our search method, suppose this is the trie that we have actually created, and these are the words we have added. Let me quickly go over them. So first word is pen. If you look at this direction, we have the word pen, then we have the pot. So P is common, so then there is a branch out and we get the word pot as well. Same, we have cat, cars and bed in the similar sequence, and these are the words we are trying to search. So couple of words are just regular words. Then I have added some examples with the dots in it, so because they are more complicated ones, so we can understand that. So let's quickly start to go over and see that what would be our search policy for this given trie that we have created. So for this character pot, first letter is P. So from this root we are going to see that does there a children that contains the character P, and yes, we have a child that contains the character P. So based on that, we will keep on iterating in that direction. So next character is O, so we have O as well, and the next character is T, so we have T as well. Now we don't care about this end node, because as long as we are able to generate the word that we were given, we are good up until this point. So over here we will actually return true to be the answer, that yes, this word is present inside the trie that we have created. Second word is pots. So again, for the pots, we up until this pot we are going to go in the same direction, but this S is not present as one of the children of this pot, and because we encounter an end node over here, so we can drop out immediately and we can return false in this case, that yeah, we don't have any character that matches the word pots. Now this is a little bit interesting example. So for this dot AR, the policy we are going to use is that whenever we encounter a dot to be a character, we will actually have to iterate over every single possible route using this dot to be the character and see that can we make this AR to be part of that sequence or not. So let's quickly do that, and let me clean this up a bit. For this dot AR, the strategy we are going to use is, for this particular dot, we are going to consider it that every single child of this root can be used over here, and then we will try to see that whether is there any place where second character is actually A. So first we go down this path. Okay, so P, we consider P as dot, right? Then we check that, okay, this is E and this is not A, so we cannot go on this path. Okay, now we backtrack. Now we keep this P to be dot. Now again we try to repeat the same process. This is A and this is O. So again, this is not the path we are going to choose. That is going to lead us to this answer. We come back. Now, okay, we are at this position. Again, we check this child. So this child is actually C. We consider C to be the dot. Okay. Now from the C, the next character is actually A, and all over here the next character is also A. So that is good sign for us. So now we can continue in that direction. So now from this A, we will try to see that is there a child that is actually R, and yes, from this A we also have a child that is R. And since we reach to the end of this word, we can return true in this case, that yes, this dot AR is present inside this trie that we created. Okay, so yeah, that's a wonderful news. Now let's focus on the next example. So next example is dot dot T. So for the dot dot T, actually we will have to branch out even more. So for this second dot dot T, what we are going to do is, again we are going to repeat the same strategy. We will have to go over every single child that is possible. So first we will consider this P to be the first dot. So this dot is this P. Okay, now from this P, we will also consider two child to be separate dots. So for both the childs, okay, this is going to be the first dot. So we are good up until this point, but this value is actually not T, this is N. So we will have to backtrack. From this E, we do not have any child, so we will again backtrack and we will come back to this P to be one dot. Now from this P, we still have one more root that we haven't considered. So we will consider this O to be the second dot. And from this O, we actually have the last character T present, and that matches this string dot dot T. So if we go down this path, we will be able to generate this word, and that's why we will also return true in this case as well. And the same thing we are going to repeat for this dot ey strategy. So for this dot ey, what we are going to do is, first of all, we are going to consider this to be the dot. We will see, okay, this is E, so that is good, but this is not Y, so again we cannot go down this path. Again, this is dot, this is not the path, this is not the path, this is not the path. So this dot ey is actually not present inside this entire trie block that we have created. So over here we will return false, but before returning false, we will actually check every single possible route to see that whether we can find a match or not. Okay, so that is how we are actually going to implement the search mechanism. Basically, the only tricky part is to take care of the dot values. Apart from that, it's pretty simple. Now let's talk about time and space complexity. So for the add function, the time complexity is actually going to be big O of n, that depending on the number of characters that are presented inside the input. And also for the space complexity, it's also going to be big O of n, depending on the size of the input. For the search mechanism, things become a little bit tricky. Over here, the time complexity is actually going to be big O of 26 times n. Why 26 times n? Because remember, for any given dot, there can be 26 child of any particular root element that we might have to iterate over, and again, in the bottom we might have to keep on repeating the same process, right? So basically, the maximum time and space complexity we might have to go over is going to be n times 26, but since 26 is a finite number, we can also consider this to be big O of n only. Okay, and for the space complexity, it's also going to be the same. It's going to be big O of 26 to the power of n. So for this problem, we are being asked to implement three things: word dictionary, add word, and search method. The thing is, before that, we will actually have to define a trie node. So I'm going to create a separate class for to defining a trie node, where every single trie node has a different set of children, and we can easily quickly look up those children because we are actually using hash map to define them. Okay, now from our main method, first of all, we are going to create a new trie node. So now to implement our word dictionary, first of all, we are actually going to create an instance of this trie. Now for this add word method, first of all, we'll have to create a node. So we are going to create a trie node. We are going to run a for loop across the given word. If the current node, if that does not contain any children with this character, then we will have to create a new entry inside our node. And if the entry exists for this given character, we are actually going to go to the next element, and in the end we are going to define node.word to be true. So before we start our search method, we are actually going to create a helper method called search in node, that is going to take the input word and the trie node as the input, and that is going to help us to iterate over the given trie node. So first of all, we are going to create a for loop to iterate over this given word, and inside this given word we are going to iterate over character by character. So I'm also going to create a new character variable. So first of all, we are going to check that if the given node or does its children contains this word or not. If it does not contain, then we are going to check that whether the given character is dot or not, and if that is the dot, then we might have to iterate over all the subsequent characters of this node. Once we determine that the children does not contain this character ch, we are going to check that whether the ch is actually a dot or not. If that is dot, then we are going to run a for loop across all the children for every single character value, and then we are going to define a new trie node called child, and basically we are going to call this search in node method iteratively for the next character in that particular word, because remember, we are already eliminating the dot character and providing its child as the trie node, and we will keep on repeating this, we will keep on iterating this process, and we are going to return true. If that is not the case, and if this given ch character is not a dot, then in that case we can return false immediately. Somehow this ch is actually a child of this node. If that is the case, then we simply need to iterate over the next value inside this given node, and in the end we simply need to return that whether the node.word is present or not. And remember, we are storing this node.word value inside our this add word method as well. So the moment we identify a matching word, it would return true, otherwise it would return false. Now from this our search method, all we will have to do is we simply need to call the recursive search in node method that we have created, and as the input we are going to provide the value of the word, and we are also going to initialize a new trie node, or we are also going to provide the trie node that we initialized earlier, and that's it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. Okay, seems like our solution worked as expected. It was not the fastest solution in terms of time complexity, but in terms of space complexity, it was pretty efficient. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do binary tree maximum path sum lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, DoorDash, Facebook, Microsoft, Google, ByteDance, TikTok, Snapchat, Twitter, Apple, Uber and LinkedIn. So that's why I am paying my utmost attention. I hope you also enjoy the video. So despite being a hard problem, this is a very well liked problem on LeetCode. Basically, we are given the root of a binary tree and we need to return the maximum path sum for that particular non-empty path. So we will have to understand a couple of terminologies over here. We will have to understand that what a path sum is, and before we understand that, we will have to understand that what a path is. Lucky for us, we are given definition of both of them. So a path is a binary tree sequence of nodes where each pair of adjacent nodes in that particular sequence has an edge connecting them, and we are also told one very important thing, that any single node in that sequence can at most appear once. We are also given the note that it is not necessary that path has to go through the root of the node. Okay, so over here I have drawn a couple of different trees and I'm going to show you some examples of what a valid path is and what an invalid path is. So first of all, this is a valid path. And for that, we'll have to understand that why this path is a valid path, because all the three nodes that are connected in this particular path, they are adjacent to each other. They all have an edge connecting to them and they all appear at most once and nothing more than that. Now, this is also a valid path and this is also a valid path. This is also a valid path and this is also a valid path. Both paths are valid as well. And the path that looks like this is also a valid path, and the path that looks like this is also a valid path. Now let's see some examples of an invalid path. Suppose I start up my journey over here. I go up, I go down, I go to the left child, and then again I try to go to the right child. Again, this is an example of an invalid path because this node appears twice as well. Now we know many examples that what a valid path is. Now let's see that what the problem is actually asking us to solve. After understanding the definition of a path, we are going to understand the definition of a path sum. Basically, it is the sum of all the nodes that are present inside this given path. So that is actually quite simple to understand, and the problem is actually asking us to find the maximum path sum that we can make out of given binary tree. So now I have drawn three different trees to understand the maximum path sum for each one of them. So first of all, for this particular tree, the maximum path sum is going to be this path. And why? Because all the nodes are positive, and if we take the sum of these three nodes, it's actually going to be 5 plus 4 plus 9, which becomes 18. And this is what we need to return in the answer. If we take the second example, things are not as easy as the first one. Why? Because we are dealing with a negative value over here. So in this case, even if we try to do the same path that we had drawn over here, this won't work because the sum of this is actually going to be, which is not the most optimal path we can achieve. The most optimal path in this case is going to be this one, and the sum is actually going to be 5 plus 4 equals to 9. And in this case, we will have to return 9. So in this case, the maximum path actually is going to be this one between these three nodes. Why? Though there is a positive value over here, if we were to include this positive value, the path we would make would looks like this, and that would actually go through this root value which has the value of negative 11, which actually brings the total path down or total sum down. So that is why it is not in our best interest to include this node, and that is why the maximum path in this case we can achieve is amongst these three nodes, where the sum is actually going to be 10 plus 8 plus 2 equals to 20, and that is what we need to return. Now before we come up with the optimal solution, I'm going to show you a few different concepts with various examples. So first of all, we have an example of tree that looks like this, where in this case all the nodes are positive, which means things are a little bit easy for us, and our aim is to find the maximum product sum we can achieve, right? So the idea is at any given portion we have the root information. Now from this root information, what we are going to do is we are going to see that what this left subtree has to offer and what this right subtree has to offer, and then addition of all of them should give us our maximum product sum. So in this case, this left subtree does not have any more children. It only has one node, which means it can, the maximum value it can contribute towards the maximum path sum is going to be 5. So we have the value 3 already from this root. Then we gain this 5 from the maximum path sum, and then again we gain this 2 from this right subtree. So the total maximum path sum we can achieve is going to be 10, which is the answer in this case. And since all nodes were positive, it is in our favor to include all the nodes. So that is one way to do it, right? And this is a very simple example, so we are able to understand it quickly. Now let's try to see that what would be the approach in a little bit more difficult scenario. So suppose we are given a tree like this. In this case, we actually have a negative value. So if we apply the same logic over here, this left subchild has -5 to offer, this right subchild has +2 to offer, and this root value is actually 3. So maximum path sum based on the previous logic would actually become 0 if we just do sum of all the values. But that is not what we are going to do. We are also going to check at any given moment that whether the value that is being contributed, if that is less than 0 or not. If that is less than 0, immediately we are going to discard this value, which means that we are not going to consider this -5 to be part of this maximum product sum. And in this case, what we are going to do is we are going to do this 3 plus 2 because both values are positive. So in this case, the answer we are going to get is 5. So we gain one more important thing, that whenever we see minus values, we are going to ignore that from our maximum production because they don't add any more value over here. Now one more thing we need to consider. What if we have multiple nodes, and then what should be our approach in that case? Okay, suppose we are given an example like this. In this case, what should be our approach? Well, we want to find the maximum path sum. So again, we are going to repeat the same process. We are going to see that for this root node, what does this left subtree has to offer? It has to offer maximum 5 value. So we are good up until this point. For this right subtree, actually we will have to calculate that what is the maximum value it can offer. And how we can do it? We are actually going to take this root value because that is going to be the part of this right subtree for sure. So we already have value as 8 over here. Now from this 8, we actually have two options to be included for our maximum path sum. We can either do 8-2 or we can do 8-1. So in this case, obvious choice is going to be 2 because this value 2 is actually greater than with this value 1. So in this case, we are going to ignore this 1 and we are going to keep this 2, which means that we can do 8 plus 2 to be 10. So in this case, we can determine that this actually has the value 10 to give towards maximum path sum. Now the question will come to your mind is that why in this case we only choose value 10 and why not we chose value 11? Well, what if under what circumstances can this value become 11? It can become 11 if we include all these three values to be part of this maximum path sum. But we already know that this goes through the root value, which means that if we were to include all these three values to make the value 11, it won't work, because then the path would look like this. It would go from 5 to 3. Okay, so far we are good. Then again through 8. Now from this 8, we cannot include both 1 and 2, because suppose we try to do it, we include this 1 and then we try to go back to 2, we come up at this 8 again, and we know that that cannot be part of a path sum. So that is why we only have the option to choose either 1 or 2. So that is the important detail over here. That is why for when we were calculating the maximum contribution this right subtree can make, we only had two options. Either we could do 8 plus 2 or we could do 8 plus 1, but not both of them. So just remember that is why I showed you this example. So in this case, the maximum contribution we can get from this right subtree is going to be 10. So now let's calculate the maximum path sum in this case. So the maximum path sum is going to be the root node is 3 plus this left subtree can contribute value 5 and plus this right subtree can contribute value 10. So the answer is going to be 18, and this is what we need to return in this case. So far we have understood, we had gained very good understanding of many different cases. Now let's consider one more case where the things become a little bit more interesting. And why it becomes interesting? Because so far we are under the impression that we have to take this root value as part of the answer. But what if that is not the case? What if we encounter some possibility where this root value does not need to be part of the main maximum path sum that we take? Then how do we approach that? So let me quickly show you an example for that as well. Okay, this is the last complicated example. Now in this case, we are again going to apply the same logic to find the maximum path sum, but we are going to do some interesting things. So first of all, we have this root value to be -3, right? Now we are going to see that what is the leftmost contribution it can get. It can get 3 as the contribution in this case. Now again, for this portion, we are going to see that what is the rightmost contribution it can get. The rightmost contribution it can get in this case is going to be this 8 plus 2. So 8 plus 2 is going to be 10 so far, right? Now if we see over here, actually this is not the most optimal way to approach this. Why? Because this path actually gives us the maximum path sum. So let's see that how can we actually determine that. Well, when we are traversing, we are actually going to have a variable called path to keep track of what is the current maximum value we have found so far, and whether do we need to include a new route. And new route in this case is going to be the condition where we actually refrain away or move away from the original route we were using, because if we were to use this route node, there is no way for us to use all of these three nodes. So that's why what we are going to do is, we are first of all going to see that if we use this current route, what is the maximum value we are gaining. So the maximum value we are gaining in this case is going to be 3, which is this one, plus 10, which is the contribution we can get from this right subtree. So 3 plus 10, and let me get rid of this maximum path sum for now. So 3 plus 10 plus whatever the root value. So root value in this case is minus 3, which is in this case the total value is going to be 10. But now when we are traversing, or when we were calculating the maximum contribution we can gain from this right subtree where the root node is actually 8, the value maximum we can gain from over here is actually going to be this value 8, plus it has the its left subtree is contributing value 1 and its right subtree is contributing value 2, so which both are positive values, and their total is actually 11. So this is 11 and this is 10. Then why are we so keen to keeping this root to be part of the optimal solution? We should not put it in the maximum path sum, and this is exactly what we are going to do. Then we are going to choose a new path, and this new path, the value is 11. So then we are going to have a maximum path sum variable where we are going to keep on updating the value, and we are going to update the value to be 11. And now it does not have any further no more nodes to check for, and then we are going to return this 11 to be the answer. And at any given moment, whenever we find that the new path we are getting, that gives us better answer than whatever the previous answer we were getting, then we would update the new path and we will update the value of the path variable. So that is one tricky part that we have to understand in this question. And now let's see that after understanding all the concepts, now let's see that what would be the way to solve this problem. The idea is, let me clean this up a bit. Now I'm going to use the same example to quickly walk through this problem. So first of all, we are at this root position. What is the left contribution we can get, which is 2. The right contribution we can get, in this case it's going to be 10. We actually calculated all of them. Now the sum of these these three is actually going to be 10 only, but when we were calculating that, we had this path variable where we actually calculated the value of this to be 11, and we updated this path variable. And then we are going to have this maximum path value where we are going to keep track of the maximum path we have found so far, and in the end, because it does not have any more children, we are going to return the maximum path to be 11, and this is what the answer we need to return. So basically we are taking a bigger problem, and then we are dividing it into bunch of different parts. That for this root we are actually trying to calculate this left subtree and right subtree. Then again for this root value, again, we are again calculating this left subtree and right subtree, which means we are solving this problem recursively, and that is how we are going to approach it. And also let me show you the time and space complexity. So time complexity in this case is actually going to be big O of n. Why big O of n? Because at any given moment we will have to iterate over all the nodes that are present inside this given tree, and the space complexity is going to be big O of h, where h is the height of the tree. So first of all, we will need a separate method called max gain to calculate that what is the maximum value we are gaining. So for that, we are going to create a new method that takes in a node as an argument. We will also need a maximum sum value. So we are going to initialize it as global variable. We are going to assign it to the most negative value possible. So okay, now let's start implementing our max gain function. So first of all, we are going to have the terminating case that if the given node is equal to null, we will return 0. If that is not the case, we will need the values of left gain and right gain for any given tree node. So we are again going to call the recursive function for that. We are going to create a variable called price new path that we are actually going to calculate by using the node value plus whatever the sum of left gain and right gain is. Now that is done, we are actually going to calculate the max sum. We are going to compare it with whatever this new path we are calculating. And once that is done, basically all we will have to do is simply return the node value with whatever the maximum value is amongst this left gain or right gain. From this max path sum method, we will have to call this max gain function. So let's do that. After all the calculation, we are simply going to return whatever the max sum we are able to achieve. Okay, and now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient and faster than a lot of other solutions. And I would be posting this in the comments so you can check it out from there. So today we are going to do serialize and deserialize binary tree LeetCode problem. And if we see some of the companies where I want to get a job who already asked this question, there are companies like Amazon, Microsoft, LinkedIn, Uber, Google, Facebook, DoorDash, TikTok, Apple, Snapchat, Splunk, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Hello friends, the reason I have not been uploading in recent days is because I just had twin baby girls. And so yeah, that's the update. And now let's move on to the video. So LeetCode thinks that this is actually a hard problem, but in my opinion, this is not a hard problem. It's actually very creative problem. Basically, we need to serialize and deserialize the given binary tree. Now, first we'll have to understand that what does serialize and deserialize means. Well, serialization is the process of converting the given data structure, which is tree in this case, and we need to convert that into a sequence of bits so that it can be stored in some memory or file buffer, and then we can transmit it across any network. Now in this problem, basically we need to design an algorithm where we are actually serializing and deserializing a binary tree. So serializing means that first of all we are finding a way to convert the given binary tree in some sort of bits, and in this case we are told that we need to convert it in strings, so we are familiar with that. And then deserialize means that we are given this string and we need to write an algorithm to convert this string back to a binary tree. So we'll have to do both the things. And if you see this problem, this is actually very similar problem that we did earlier with strings. This is the solution of that problem, so go and check it out first. We are also given a clarification that we can be as creative as we can with the serialization and deserialization process. So we can have different way of serializing the tree and different way of deserializing the tree as long as we maintain the tree data structure. So let's see that what is the approach I am suggesting, and you can also come up with your own creative approach. Well, basically in this problem, we are only given the root of a tree, and then somehow we will have to go over the entire tree and then traverse it, convert this given root and all of the entire tree into a string. And after we have converted it to string, we will have to find a way that suppose if we are given the string as the input, how can we convert from the string this binary tree as well? So we are doing both the processes. So the important thing in this case is that we will have to traverse over the given binary tree. There are mainly two strategies to traverse over the given binary tree, DFS and BFS, and I have explained this very carefully in the previous video. You can check it out over here. So basically in this video, what I'm suggesting is that we actually go with pre-order approach with using DFS to serialize and deserialize this given binary tree, and I would be showing you that what is the process we are following. So first of all, we are going to serialize this given tree, which means we are going to take this binary tree and we are going to convert it to a string. Now, as mentioned earlier, we are going to use the Preorder Traversal for that. So if you are not familiar with the Preorder Traversal, basically we visit the root node first, then we visit the left child of this root node, and then we visit the right child of this root node. And that is how we are going to end up creating the string from this given binary tree. So let's see that in action. So first of all, let's create a variable called s or string where we are going to store the string value. So first of all, we are going to visit the root node. The root node in this case is 1. So we are going to add an entry called 1 over here. Now we need to visit the left child of this root, and then we need to visit the right child of this root. Now remember, this is actually a DFS policy. So in the DFS, we go in the depth first. So first of all, we are going to visit the left child. So left child in this case is 2. So we are going to add an entry that 2 is the left child over here. And then again for this 2, because we still have left child left, so we are going to visit that. So for this 2, the left child in this case is actually 4. Now for this 4, we don't have any more left child and we don't have any more right child, which means that first we try to visit the left child. For this 4 there is no left child, so we enter a value called null over here. And then for this 4 again there is no right child, so again we add value null over here, saying that for this 4 the two left child and right child is actually a null value. Now after that we still have nodes left that we haven't visited. So now for this node 2 we have this node 5 and it's right. So again we are going to enter the value 5 over here. After entering the value 5, we are again going to check the left child and right child for this 5. So left child in this case is null, and again right child is also null, so we will add 2 more entries, null, null again. And now we go back. So now we have visited all of these nodes, but the thing is we haven't visited the right portion of this original root node. So again we will have to iterate over the right subtree. So right subtree in this case is going to be 3, so we add 3 over here. Now for this 3 again we don't have any more children nodes, so again we add 2 null values. So this is the answer in this case that we have to return for this given tree, that this is the string value that represents this given binary tree. Now let's see that what would be the deserialization process. So now we are going to work upon the deserialization. So basically we are going to convert string into binary tree. So the idea is this is the string we generated from the serialization process. Now again because we are using preorder traversal, we are actually going to apply the same logic. So we are going to treat the first node to be the root node, then the next node would be the left subchild of this root node, and the next node is going to be the right subchild of this root node, and we are going to keep on iterating this process in reverse order. So the idea is that first of all, okay, we identify this node. So this node is actually our root node. Okay, so root node is actually 1 in this case. Now again this 2 is actually the left child of this root node. So because this left child exists, the next node is again going to be the left child of this node 2. So again we are going to create a node 4 that is left child of this node. Now for this 4, the next 2 nodes are actually null null. So because we encounter 2 null values, which means this 4 does not have any more children, so we can just ignore that. Okay, now we still have a node 5, which means that this 5 is actually the right child of this 2, because we have already visited the left subtree of this 2. So now because we are done with the left subtree, now we are visiting the right subtree. So we are going to create one more entry 5 over here as the right subtree. And again we have 2 more null values, which means that this right subtree is done. Now we don't have any more values. Okay, now we still have values, which means that this actually refers to a root node where we haven't visited the left and right subtree. Because remember that this is the left subtree we have visited for this 2, and this is the right subtree we have visited for this 2, but we haven't visited the right subtree for this original one. So now we are going to do that. So now we are going to add one more entry 3 over here, which is the right subtree of this original given one, and this 3 actually has null values, which means 3 does not have any more children, so we won't be adding any more entries over here, and we can just ignore that. Now we have reached the end of the string. So because we have reached the end of the string, we have created the binary tree that we are supposed to create, and we have completed the deserialization process, and we have converted the string into the binary tree. So this is the approach we are going to take. If we see the time and space complexity in this case, for the serialization process, the time complexity is actually going to be big O of n, because we have to iterate over n characters that are present, and the space complexity is also going to be big O of n, because we will have to create a string where we are storing all the n values. Now for the deserialization process, again the time and space complexity remains the same. Now we will have to create two methods for serialize and deserialization. So first of all, we are going to work upon serialize process. So I'm actually going to create a new public method that returns a string where recursively we can apply the preorder traversal, and as an input it is going to take the root value, and we are also going to pass the string value. Now inside this recursive function, first of all we are going to find the terminating case. So if the given root is equal to null, then simply add the value to the string as null. If that is not the case, which means that root still has some value and it could have left subtree and right subtree, so now we are going to call the recursive function. So first of all we are going to add the value to our string. Now we are going to call the left subtree and right subtree. So we are again going to call this recursive serialize method. Again we are going to repeat the same process for the right subtree. Once this ends, we are simply going to return the string. Now from our main serialize method, all we have to do is just call this recursive serialize method and return whatever the answer we get. We are going to pass in root as an entry, and we are going to pass in an empty string. So now we are done with our serialize method. Now let's work upon deserializing method. Now again, for the deserializing process, first of all, we will have to create a recursive method to iterate over this given string data, and then we are going to convert all the string values into binary tree. So we are passing a list of strings in this case for this recursive deserialize method. And now first of all, we are going to work upon the terminating case. If the given node is null, we can simply remove the value and then we can return null. Okay, if that is not the case, first of all, we are going to note the whatever the value of this current string is, we are going to treat it as a root node, and then we are going to call the left subtree and right subtree. So we are going to create a new tree node called root. So whatever the current value of this string is, we are going to treat it as a root node. Then after adding the root node, we are actually going to remove that value. Okay, now for the left value, we are again going to call this recursive deserialize method, and that should be it. After this ends, basically we should have a root variable, so we can simply return root. Now from this main method, first of all, we will have to create an array of string where we are actually splitting the string based on the comma that we initially created. After doing this, we are actually going to convert the string array into a list of strings. Now we will simply return whatever the answer we get by calling this recursive method. That should be it. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. So I will be trying to see other faster approaches and see I can make a future video on that. But so far you can find this code in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search to lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Uber, Microsoft, Google, Snapchat, Facebook, Apple, Twitter, TikTok, Bloomberg, Spotify, Twitch, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode hard problem, and basically we are given an m cross n matrix of characters. Now, and we are also given a different list of string called words. Now we need to return all the words that are present on the given board. We are also given one more thing, that each word must be constructed from the letters that are adjacent to each other. So, and we are also given the definition that what adjacent cells are. Basically, any cells that are horizontally or vertically neighboring to each other, we can consider them to be a part of the consecutive sequence series, and we can use them to create words. So let's try to understand this with an example over here. Over here we are given a 4x4 matrix, and for this matrix we are told that these are the list of words. We need to check that whether they are present inside this given matrix or not. So if we try to just look at this example, basically we can see that this first word oath is actually present over here, where O, A, T and H, they are creating or forming this word, and if you see, they are all sequentially adjacent cells to each other. So that's why we can use them to form this words and see whether it's present or not. So in the answer, first of all, we are going to add the word oath as one of the answer. Then if we look at the answer, we can also find this word eat to be present. So E-A-T, that is present in this manner. And again, though this is on the left side, this is not the conventional way to write it, but still based on the adjacent cells, we can actually form this word eat, and that's why this eat is also going to be part of the answer. So we'll add eat in the answer as well. Now for this two, P-E-A, P and drain, these two are not present inside this given matrix, so we will not include them in the answer, and this is the answer we will have to return. So basically it is one kind of a word search game or word search puzzle. So that is why the name is word search 2, and this is the little bit of advanced version. So first we'll see that what is going to be like a basic, very trivial approach, and then we will try to improvise using a different set of data structures. Okay, so most basic idea we are going to have is that we will start iterating over all of the characters that are present inside this m cross n matrix, and then for every single character we are going to see that whether that matches with any of the starting words or not. If we find a potential match, then we will try to find the subsequent character and the neighbors of that particular character to see if we are able to generate any exact word or not. And the moment we do that, we will actually put it in a new variable called answer, and that is how we will be able to generate our answer. So let's try to see this in action. So first character in this case is X. So X matches with this character over here in the given set of words. So next we will have to see that whether any neighbor of X is actually Y or not. Neighbor of X is actually H and A. We do not find Y over here. So because we do not find Y over here, this X does not lead to anywhere. So we can mark this as visited. That does not lead to any answer. Next character is H. So H matches with this first character. And then we will have to see that whether B exists as one of the neighbors of H, and B also exists as one of the neighbors of H, and then the subsequent character O also exists as one of the neighbors of B. So in this case, this HBO is actually a complete word we are able to make based on subsequent characters that are present adjacent to each other inside this given matrix. And because of that, we are going to create a new variable called the answer, and in the answer we are going to add the value HBO over here. Now we will start iterating over this A. So again, A is the starting point over here, and next character B and C, we are able to generate this pair using sequentially iterating over. And if we see over here, we can also generate this A, B, C in this fashion. Now this character is Y. So again, Y is not part of starting character of any other word, so we cannot do anything about this. Next character is again C, that we have already visited, so we don't need to visit this. And next character is Z. Z again is not the starting point of any of these characters. So in this case, this is the answer we are going to have, and we can return this one. This solution works as expected. There are no issues with this one. But if you just see, we only have a 3 by 3 matrix, and for every single character, in the worst case scenario, we might have to iterate over every single word and check that whether it matches the starting word or not. We can maybe simplify using a hash map, but the thing is, this is still going to lead to a very bad solution. In terms of time complexity, this is going to be disaster, because for every single character, we might have to iterate over every single word that there is. And once we find a match, then we will have to iterate over all the neighbors of that particular character as well. So that leads to nowhere. So let's try to see that where we can find a better time complexity. And the solution to achieve a better time complexity is actually using a new data structure called Trie. Now I have already extensively worked on Trie, and you can find all of those solutions over here. Check out this video if you want to learn that what a Trie is and what are its applications. Now let's see that how we are going to use Trie in this case to improve our performance. Okay, so the previous example we see, basically what we are doing is we were iterating over every single character, and then we were trying to see that whether that character matches the first element or not, and sequentially we will have to check every single word that was present. And if we find a potential match, then we will have to check all the neighbors to see if the next consecutive element is present or not. And that was the major reason that why we were having a disastrous time complexity. So in order to improve that, if we can find some way to eliminate this checking procedure, that for every single character we might have to look up all the elements or all the words that are present, because imagine if there are million words present, we might have to check million times, and then that is going to be very disastrous. The idea we are going to use is that whatever the words that we are given, we are actually going to convert these into a Trie. And because we are converting them into a Trie, for any character, searching that whether it is the starting point of any word or not becomes pretty easy for us, and we can actually do it in nearly constant time. Because in the Trie, it is very fast and efficient to find that whether any word exists or not, and if it exists, it is very easy for us to iterate over that particular word or not. So first of all, let me quickly create a Trie block based on these three words. The Trie block is going to look like this. So based on the word that we were previously given, we actually created a Trie block. And now using this Trie block, we are going to make things pretty easy for ourselves. Basically, we are going to iterate over in the same fashion for the given matrix. But this time, all we will have to see is to look up in this Trie that whether the current character, if that is any children of this given root node or not. And if that is the case, we will keep on iterating. So first we find this character to be E. E is not part of any children, so we can ignore that. Next one is F. F is actually part of a children. So okay, now we have found F to be part of the children. Now we will have to see that what is the next character in this Trie block. So this next character is A. So we will have to see that whether any neighbors of this F is actually A or not. So we will have to check on three sides, and we find a match over here that this is A. Okay, now again next character is A. Again this neighbor is actually A. Okay, now this character is N. So again neighbor of this A is N present over here. And again the next character is G. So G is also present over here. And since we have reached to the end node inside our trie, because of that we can conclude that the whole word was actually present inside this given matrix, and we can return true in this case, and we will add it to our answer list. So inside the answer list, the first word we are going to add is FAANG, that is present inside this given matrix. So see how easy it is for us to find these things. And okay, now the next character is R. R is not children of any of these root nodes. Next one is T. T is also not a children. L is not a children. These are all visited. Now this G. G is actually a children. So now it becomes easy. Now we will have to start iterating over. Okay, so we are at this position G. Now the next element is O. The next element is O, and O is also a neighbor over here. Okay, so which is good. Now the next element is O. Again, O is a neighbor over here. So which is good. Now this next element is G. G is also a neighbor of this O, right? So we are good up until this point. Now we have to find this L. Now, if we look at this G, we do not find L to be a neighbor of this G. So because of that, we will actually have to roll back, and we cannot move forward with this path. So now we would have visited this G, and that did not lead us to anywhere. So again, we will start with our routine procedure. Okay, now this next character is O. O is not starting point of anything. T is also not starting point of anything. G is, we have already used it. Now this is again G. So again G is the starting point of this one. Next character is O. O is present over here. Next character is O. O is also neighbor of this one. Next character is G. G is neighbor of this one. Next character is L. L is neighbor of this one. And next character is E. E is the first character. And because we reached to the end character over here, we can conclude that Google is also present inside this given matrix, and we will add it to our answer. So we will add one other entry called Google. Okay, and now next again this character is L. So L does not lead to any children of this root node, and F does not lead to any children of this root node. So in the answer, we are going to return this FAANG and Google to be the answer, and this would be the most optimal way to solve this problem. Remember, because we used a trie block, things becomes much more faster for us, and we can immediately look up that whether any single character that leads to an answer or not. Okay, now let's do the tricky part. We will have to do the time and space complexity analysis. So for the time complexity analysis, it's actually a little bit tricky. The first thing that is a given fact is that we will have to iterate over every single character that is present inside this given m cross n matrix. So that's a given fact. Suppose that the total number of cells that are present are actually m. So now, okay, we already know that is whatever the time complexity is going to be the factor of m. Now for this particular m, imagine that for any particular character, what is the maximum work we will have to do in the worst case scenario? Well, the maximum work we will have to do in the worst case scenario is that any particular character, suppose this F matches this character that is present. Now, whenever we find a potential match, we will have to look for the next element in all three directions of that particular word. So suppose this O was a potential match, we will have to iterate over all four directions in any given case. So for any single cell, we might have to iterate over in all four directions, and for all four directions, the number of traversal that we will have to do for each one of them would depend on the next three or the next remaining three characters. Because remember, for this Google, suppose we find a match, this O to be a match. Now the moment we find this O to be a match, again we find this O to be a match. So now because we find this to be a match, we do not have to look for this particular element. We will have to look at the remaining three positions. So then we will have to, for any single character, we will have to look in the four directions, and for all the subsequent elements, we will have to look in the remaining three directions, and that we will have to do depending on the length of that particular word. So for the remaining three elements, we will have to iterate over to the length of that. So that's why 3 to the power of L minus 1. And why minus 1? Because for this first character, we are actually looking in the worst case scenario in all four directions, and for all the subsequent length parameters. So suppose for this particular FAANG, for this F, we might have to look in four directions, and for this A, we only have to look in the remaining three directions because one adjacent cell is already F. so that we do not have to look at. So this is going to be the time complexity. So if I write the final time complexity, it's actually going to be big O of m into 4 times 3 to the power of L minus 1, and that is the final time complexity. This is a very difficult time complexity analysis. So yeah, it gives you an idea that why this problem is pretty popular. If we see space complexity, that is pretty simple. Space complexity depends on the total number of words that are present. So suppose we sum that up to big O of n, where m is the total number of characters that are present in the or initial word list. So after doing this time and space complexity analysis, now let's move on to the coding. Before we implement our solution, we are actually going to create our class Trie node. In the class solution, we are going to define a couple of global variables. Now inside the find words method, first of all, we are going to initialize our try block, and we are going to add all the words to our try block. After creating the try node, now we are going to start working on backtracking, starting with each cell in the board. So first of all, let's create the board variable. And now we are going to initialize couple of loops to iterate over this full board matrix. So now for every single position inside this given matrix, we are going to check that whether that is actually any of the children of this root try node that we have created. And if that is the case, then we will create a helper method called backtracking, where we are going to iterate over all the adjacent cells of that particular row and column position, and also that particular entire DFS traversal for that particular branch inside our try node. After this loop ends, basically we should have populated our answer inside this answer variable that we have created, so we can simply return that. And now let's create our backtracking method. So this is going to be our recursive method. First of all, we are going to define a couple of variables. First of all, we are going to check that whether the current node is actually a word or not. If that is a word, we can immediately add it to our result. Okay, if that is not the case, we will have to start doing our traversal. So how we are going to do our traversal? Remember, whatever the current row and column is, we cannot use the same word again. So we are actually going to mark this as hash in a way for us to identify that that is the node we have already visited. Now for any given row and column, we will have to iterate over all of its neighbors. So we are going to use couple of variables to our advantage. Now with the help of row and column offset, it becomes pretty easy for us to iterate over all the neighbors of any given node. So now we are going to run a for loop, and we are going to iterate over all the neighbors of given row and column position. First we check that whether our new row and new column, if they are going out of bounds or not. That is the case, we just simply ignore that. Otherwise, if we are at the correct neighbor, we need to check that whether that neighbor is actually subsequent character that we have already stored in our try or not. And if that is the case, we are going to call our backtracking method again. Now after our exploration ends, basically we will have to put back this hash to its original position, and that should be it. There is one more optimization we can do, and that is to incrementally remove the leaf nodes, which means that whenever we identify that the current node's children, if that is empty, then basically we can just remove that from our parent. That should be it. Let's try to run this code. We will also have to update the value of the node in the else condition. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently. I would be posting this in the comments so you can check it out from there. Thank you.